So good morning, everyone, and welcome to the third day of our intensive course on metal halide perovskite materials and their optoelectronic mainly applications. So we are now starting the third day of the school of the intensive course, which is devoted to applications such as light-emitting diodes, photodetectors, field effect transistors, and lasers. So as a speaker today, as our first speaker today, it's a great pleasure and honor for us to have Dr. Murali Gedda from King Abdullah University of Science and Technology, KAUST, Saudi Arabia. A short introduction about Murali. So he received a bachelor's degree from Andhra University in India, and then he moved to Department of Physics in the same university to acquire a master's degree, and he obtained his PhD degree in physics from Indian Institute of Technology from Guwahati in India. Then he moved to King Abdullah University of Science and Technology in Saudi Arabia for a postdoctoral fellowship to work on solar and photovoltaic engineering research center, the KAUST Solar Center. So the topic of Murali is high efficiency perovskite organic blend light emitting diodes featuring self-assembled monolayer as Hole-Injecting layers. So it is, as I mentioned, a great pleasure and honor to have you here with us, Murali. So please share your screen and start your presentation, and if possible also if you can switch on your camera so we can see you while you are speaking. Thank you.
Yeah, sure. Thank you, George, for a nice introduction. So let me share my screen. Can you see my shared screen?
Yes, can you put it please in presentation mode?
Yeah, sure.
Full screen.
Yeah, sure. How about now?
Yes, great. Thank you. You have 45 minutes for your presentation and then another 15 minutes for the Q&A session.
Okay, perfect. Yeah, I hope think I'm audible, right?
Yes, correct.
Thank you, George and Costas, for this opportunity. My background is basically current background is on perovskite based photovoltaic and non-photovoltaic devices. The major stream is like blending the perovskites for the better performance. This presentation consists two sections. The first section I would like to discuss about the influence of blending on two-dimensional perovskites by explaining the influence in terms of crystallinity and charge transport, and also the demonstration of device. And the second chapter, second part consists of the influence of this small molecule on quasi-two-dimensional perovskite, and then and also the important role of self-assembled monolayers for high efficiency light emitting diodes. Before going into the much details, I would like to give a short introduction about the materials. So typically this perovskites consists ABX3 structure. So these materials are belongs to simple cubic structures. The stability of this perovskite structure depends on the Goldsmith tolerance factor, which is determined from the ionic radius of various ions involved in it. So when the A side cation size increases, then it leads the perovskite three-dimensional lattice leads to deform and gives various lower dimensional features such as zero-dimensional, one-dimensional, two-dimensional structures. The three-dimensional perovskites are known for very good electronic and optoelectronic characteristics. On the other hand, these low dimensional materials are known for better stability with the benefit of quantum confinement effects. There is an intermediate class of perovskite system, which is a quasi two-dimensional perovskite system, which has the features of both three-dimensional as well as two-dimensional quantum confinement and stability effects. As you can see here, apart from their fascinating features, there is a structural and chemical flexibility that we have. So there are a lot of wide variety materials are available. Due to this reason, these materials are attractive for current emerging applications. However, when we have such kind of materials, when it comes to the device fabrication, the one thing is very important is their morphology and crystallinity, because these two parameters plays determinant role of the device performance. The ideal two-dimensional perovskite have this kind of well-defined charge transport pathways. But when it comes to the solution process, due to the lot of nucleation sites, we will end up seeing poorly oriented crystallites that hampers the efficient charge transport. So as it is a important issue, there are many research efforts being seen since last few years. There are various strategies have been invented and implemented in order to get the control over the film quality and the charge transport. Among various strategies, additive engineering is one of the mostly explored strategy for the solution process based materials, because of the additive can be added in the solution phase itself. So mostly the polymer additives or some other conductive carbon nanotubes have been explored in order to bridge the poorly oriented crystallites. Well, these methods have shown significant improvement in the charge transport characteristics, but the residues of these materials still can present within the film. So that might also cause some other unwanted effects. So in order to avoid that, we need a system with a fully aligned crystallites without any such residues. So motivated by the previous studies on organic blends, where the polymers and small molecules have been blended to form the highly crystalline and larger grain morphology, and they show that the enhanced field effect mobilities. And also, one interesting thing is when the blend is two molecules and processed by using solution, the films have shown vertical phase separation, where the polymer or the bulk small molecule is phase separated with the small molecule C8B, for example, in this case C8BTBT, which means the C8BTBT is not presenting within the system. Instead, it is vertically phase separated. So this is really interesting feature. That's why we would like to see that effect in this perovskite system. For that, we used two-dimensional perovskite, which is also known as a Rudolphson proper perovskite phase. So we choose one perovskite system, which is a PEA to PBBR4 and mixed with an additive C8BTBT. The solutions have been prepared separately, and then these precursors are added in the later stage in order to form the blend formulations. And these blend and neat films were spin coated on the various substrates and characterized them. As you can see this optical microscope image, there is a dramatic change, abrupt change from the neat to the blend upon introducing the small molecule. So the neat film consists various various small, tiny grains with a lot of grain boundaries. When it comes to blend, we have seen very large petal-like morphology, and then we check their crystalline quality by using X-ray diffraction measurements. So the X-ray diffraction patterns, you can see that we have seen very clear and well-spaced sharp diffraction peaks. These are the indicative of the formation of two-dimensional perovskite phase. And also we analyzed the, excuse me, can I interrupt? Sorry, I don't know what's happening. Hello?
Yes, we can hear you.
I don't know, something automatically happening, not operating anything. Actually, the slides are moving without, I'm doing anything. Okay, fine. Yeah. So sorry for the interruption. So let's continue that. So yeah, so by using Debye-Scherrer formula, we have calculated the crystallite sizes of neat and blend. So in the case of neat, we have obtained around 75 nanometer crystallite sizes. And when it comes to the blend, which is enhanced to 123 nanometer, so which is clear that the small molecule did not change the crystalline integrity of the perovskite and helped in improving the crystallinity to further extract the information about the molecular orientation and all. So we studied the two-dimensional XRD for the all three films, including the C8 BTBT, neat, and blend films. So as you can see here, the neat film consists Debye-Scherrer rings, which is the indicative of the existence of randomly oriented crystallites within the system. In other case, when it comes to the blend, we have seen the narrowed arcs and then also bright spots even at the in-plane and out-of-plane areas. So which is the indicative of improved orientation as it is depicted in the schematic C and D. The C indicates the neat case and D indicates the blend case. Well, the C8 BTBT is enhanced the crystallinity as well as the orientation, but now still the question remains is the presence of C8 BTBT. So whether it is within the system or is it also phase separated as we expected before. In order to see that, we probe these films by using X-ray XPS depth profiling. So for the convenience, we choose a particular energy zone where we can see all the significant peaks associated to the neat, blend, and then small molecule. So which is like the bromine is the bromine and lead correspond to the perovskite, and sulfur belongs to the small molecule. So the blend, in the blend film, both the perovskite features as well as small molecular features are coexisted, which means the film consists both the materials, but but we check the depth profiling in order to see the distribution in the film. So we choose argon ion gun with a constant sputtering rate, which is 0.21 nanometer per second. And after the first round of etching, which is equivalent to the 5 nanometer, the disappearance of a small molecule is seen here. So which is a clear indication that the small molecule is existed only on the top surface, which is about to 5 nanometer. The rest is highly aligned perovskite films. The further chemical composition has been realized from the depth profiling also. So here, as you can see, we precisely measured the thickness of the top layer, which is about to 5 nanometer. So now the system we got like this, as it is depicted here. So we have highly aligned two-dimensional perovskite crystallites. On top of that, there is a thin C8BTBT system is there. Then we are very curious to see the charge transport characteristics. Then we made the bottom gate top contact field effect transistor. So then we check the charge transfer characteristics. We have seen a hysteresis loop counterclockwise, which is in the counterclockwise direction when we are doing the gate voltage sweep from the positive 100 to the negative 100 and then back to the positive. This is like a typical p-type behavior, as the C8BTBT is a p-type organic semiconductor. In general, any is organic semiconductor with the less number of traps will show the hysteresis free kind of transfer characteristics. But in our case, we have seen a huge hysteresis loop with a good gate field modulation, which is order of 10 to the power 4. And also, in order to check the stability of this hysteresis loop, we have performed 100 continuous sweeping circles. So then we obtained a stable hysteresis loop, which is around 180 volts window. So upon realizing this hysteresis loop, we would like to study the origin of the hysteresis. So there are broadly 3 mechanisms are driven this kind of hysteresis in the organic field effect transistors. The first mechanism is associated to the dipole polarization because of the ferroelectric gate dielectrics. And the second one is the presence of mobile ions. And the third one is charge trapping and detrapping. So in order to check which one actually valid for our case, first we check the scan rate dependent characteristics. Then we have seen negligible change in the hysteresis loop. So in general, when we are using the ferroelectric gate material, when there are ion migration in the system, so those ion migrations are strongly scan dependent. So if there are such ion migration presented in the system, we could see a variation in the hysteresis window, but that is not clearly seen here. And when it comes to the dipole polarization, the direction of the hysteresis should be the clockwise for the p-type, so which is not the case. So that's why safely we can exclude this mechanism. The only mechanism is like charge trapping and detrapping because of the surface traps. But this mechanism is a purely temperature dependent mechanism. But we haven't seen any significant change even at the 5 Kelvin. Even at the 5 Kelvin, so we still have seen clear hysteresis. So these 3 mechanisms cannot actually explain the hysteresis that we observe in the system. So there is one more possibility that is the floating gate mechanism, where the charge trapping and detrapping happens through the quantum mechanical tunneling, which is a purely temperature independent phenomenon. So there are actually various sophisticated methods have been used for the floating gate. I'll give brief introduction like how the floating gate works. So the floating gate, like there is a semiconducting channel. So the accumulated charge carriers will be tunneled through the insulating layers into the conducting channels of the floating gate, and it will be trapped there in the conducting channels. Upon giving the enough bias, then we can release them in order to accumulate again back to the active channel. So this is the floating gate mechanism. In our case, we have naturally formed quantum wells, which is actually working as a floating gate, and then C8BTBT is working as an active channel. So when we realized that our system is behaving like a floating gate, then we measured the floating gate memory transistor characteristics by giving a writing and erasing pulse and reading at 0 volts. And we have seen very stable endurance and retention characteristics, and also the devices are withstand with even the short pulse, which is about 0.2 second. We still could see very clear modulation, current modulation, which is about 10 to the power of 3. So the overall device device mechanism is supporting the floating gate memory transistor with good retention and endurance characteristics. These kind of devices are actually useful for any low-end application. So upon realizing these kind of interesting features, so we would like to see the influence of this similar kind of small molecule on the quasi two-dimensional perovskite. So for that, we choose a quasi two-dimensional system, which is based on cesium and lead bromide. So, and then we mixed the small molecule in the solution phase. Then we studied the various characteristics, and then we demonstrated the application in terms of ferroelectric light-emitting diode. So, little introduction about this quasi two-dimensional perovskite. So, the more than these quasi two-dimensional perovskites, band gap depends on the number of semiconducting channels within them. So with the increased number, the band gap reduces. As you can see here, the formation energies of these individual phases are actually very similar. So this is the reason when we are aiming to make a particular n-numbered composition, when we process them as a film, we will end up getting the mixed phases, which means the same film can contain various other features as well, which means starting from n equal to 1 to the bulk. But this is not the disadvantage. This is a kind of advantage, because a system contains various band gap features within this film. So that can promote efficient charge transfer from the high band gap material to the low band gap, and it emits at the bulk phase. Well, when a system has such a kind of mixed features, it is very important to have a proper alignment and also enough density of individual phases. So this is, in order to achieve that, we have used this blending concept even here, and then we check the morphology of the film. So here there is a dramatic change from the need to blend, as we have seen our previous two-dimensional case, and then we examine the morphology. Then we have seen that the grain size of the blend is actually increased up to 1.2 micron, while the neat film has around 150 nanometer tiny grains with a lot of grain boundaries. This is one of the good finding, but further characteristics reveal that the blend system contains well formed layered morphology with the different features. And then we check the presence of the small molecule in the system. But here, in the previous case, we want the small molecule as the active channel, but here we want to make a LED. So in order to avoid any unwanted effects, we would like to remove the small molecule from the top. So then we have used the anti-solvent in order to remove this small molecule from the top. So we have studied it by using X-ray depth profiling, and then we have seen without anti-solvent, we have seen the clear feature of the small molecule. But when we use the anti-solvent, both neat and blend are showing the similar characteristics, which means the anti-solvent dripping while we are making the films are successfully remove the small molecule from the material. So now we have highly aligned perovskites without a small molecule on top of the film. So next we check the crystalline orientation by using grazing incident wide angle X-ray scattering. So a clear changes are observed when it from the neat to the blend. So we have not only seen the improved crystallinity, crystal orientation, and also the increased density of these individual features also observed from the from this study, as it is depicted here. So the appearance of several quasi two-dimensional peaks are the indicative of increased density of individual various other mixed features of quasi 2D perovskites. And then we check the photoluminescence characteristics and uniformity over the area. So we used hyperspectral photoluminescence studies, and we checked the luminescence at various locations, and we have seen there is no shift in the PL peak. And interestingly, this blend has shown enhanced luminescence, which is quite higher than the neat film. So then we expected to see the enhanced LED characteristics. For that, we fabricated a standard LED geometry by coating the P.PSS PSS as a hole transport layer, and perovskite as emissive layer, and TPP as a electron transport. Then we check the charge density, voltage, and luminescence characteristics. So these studies revealed the enhancement of current density in case of a blend, which is the I think feature of the increased crystallinity, and also the purity of the emission is quite good, even for the both neat and blend, even at various voltages. And also we check the hysteresis while we are scanning the voltage from the -1 to 5 and back to -1. We have seen the little hysteresis in case of neat, but that is significantly suppressed in case of blend. So this is the direct evidence of the existence of highly crystalline features with the less grain boundaries. And then we check the external quantum efficiency and current efficiency. The maximum values that we achieved for the blend are 3.32 and 7.7 candela per ampere. So these are relatively higher than the neat ones, but in order to have the further enhancement, we replaced these films using self-assembled monolayers. So in some of our previous reports have demonstrated the potential of the self-assembled monolayer in enhancing the solar cell characteristics. So there we explored two different self-assembled monolayers. One is a 2-pack, another one is brominated 2-pack. So we would like to take this advantage and like to see whether the similar kind of enhancement is possible in our case. So we replaced this P.PSS with self-assembled monolayer, and then we characterized the devices. So as we can see here, there is a big change obtained when it comes to the P.PSS to the neat, to the self-assembled monolayer case. So the current density enhancement as well as the external quantum efficiency enhancement is quite high, which is like 14.13 for the 2-pack. And then we used the brominated 2-pack for the further enhancing these external quantum efficiency. The maximum efficiency that we achieved is about 18.57. The reason for enhancing these efficiencies than the P.PSS case is the lower work function of the self-assembled monolayers, that we can expect the efficient charge transport from this lower to the perovskite layer. So this could be one reason, and another reason is we are functionalizing these self-assembled monolayers to the ITO, so which is few monolayers. So there is a proper charge balance quite possible. So due to these two reasons, we have achieved the maximum luminescence is around 45,276 candela per meter square, and the current efficiency is about 46.3 candela per ampere, and the maximum quantum efficiency is about 18.6. So these are the maximum values that we achieved for these kind of materials. So, and also we checked the color purity as a function of voltage. So we haven't seen any significant shift in the wavelength, which is good because there are reports with the voltage induced effects can cause the shift in the color. So that is not the case here. And then we compare the results and also we measured for various LEDs, and we obtained the great enhancement when it comes to P dot PSS to the brominated one. It's a great enhancement. So, and also we checked some of other like what are the other possible reasons in order to get this kind of enhancement. So the one in that series of measurements, this is the one of the measurement, the contact angle measurements. So we have seen the contact angle changes with the 2-pack, brominated 2-pack and P dot PSS. So the surface energies have been calculated. So the lower surface energy that we achieved for the brominated 2-pack and the corresponding AFM morphologies were also analyzed here. So the brominated 2-pack showed a larger and more uniform film. This could be the reason when you compare the 2-pack to the brominated 2-pack. So the difference in the quantum efficiency. So the difference could be associated to this enhanced crystallites as well as grain size. And as a final test, we check the stability of these devices. So the stabilities that we have, the enhancement have been seen when it comes from the neat to the blend, but these are not too great. So we need to work on this area. So now the work is actually underway in order to enhance the stability of these LEDs. Well, the summary of the whole concept is like the technique, the growth technique that we introduced is actually can be explored to the various other optoelectronic devices such as solar cells, light-emitting diodes, photodetectors, and lasers as well. And this is not like a specific to any material. So we have wide variety of small molecules available as well as perovskites are available. So it has a great scope to expand in this method to the various other applications. And also the self-assembled monolayers as a hole injection layers as a kind of a first report for the LED perovskite based LEDs. So which has shown great potential. So this concept also can be explored further for various other applications. The major challenges that we faced in this work is like when we introduced this small molecule into the system, the roughness of the film increased because of the bigger grain sizes. So though the enhancement we are seeing, but the rough films leads to the less yield of devices. So this is one of the important parameter one needs to work on it. And then also identifying the suitable material combinations such as perovskite and organic material combination is also important in order to take the benefit of both small molecule as well as the perovskite. With this, I wind up my talk. So this is the group at CAUS, and thank you for your patience. And now you can ask any questions if you have.
Thank you very much, Murali, for the very interesting and detailed presentation about your work and especially the LED part. So I would like now to give the floor to the audience for any possible questions or comments. I can see the first one from Mustafa, and the question is the following. Thanks. What is the difference between the quasi 2D layer and the nanoplatelet structure, since both structures use organic ligands and the film colloidal containing particles, which have both different and short order lateral dimensions? What causes perovskite aggregation when you prepare your materials?
Okay. Well, the quasi two-dimensional are like the materials which has the different n phases. The n determines the conducting channel. So even you are making a film of like a quite thick, but still it can withstand with these kind of two-dimensional features within the system. I'm not very sure about the other one you mentioned. It's a big question, but I did not grasp the complete message. George, could you please read again?
You mean about the second one?
Okay, the first question.
So the first one is the following. What is the difference between the quasi 2D layered and the nanoplatelet structure, since both structures use organic ligands and the film colloidal contain particles which have both different and short order lateral dimensions?
Okay, yeah, I got it. Yeah, the difference is this. So here the quasi two-dimensional layers with the different n values, we can make the differences look similar. What happened? They look similar, but so 1 minute. I think I can answer with. So the ligands, I'm not familiar with that work, but I can try to answer that one. The quantum confinement wise, the both will be the same, but here we can have a number of individual layers that actually decides the band gap. I'm not sure how that is with the ligands.
And what about the second part? What causes perovskite aggregation when you prepare your materials?
Sorry, what?
What causes perovskite aggregation when you prepare your materials?
You mean which is it any specific to a particular one you're asking, or can you can ask that the person can
okay, maybe I can ask the I mean there is another comment. I mean the spacer might be removed during the process and blending, and you will have the bulk material again.
Okay. Yeah, that's not the case as let me give it. Yeah, so that's not the case because this C8BTBT is actually not chemically interacting with the perovskite system, and moreover this we are making a separate precursor. So we are already forming the perovskite and then say BTBT precursors, and then we are giving the separate different volume ratios. So we haven't seen any replacement of these ligands or removing of these ligands. We haven't seen, and also this X-ray XRD profiles are clear evident that this is what means this clear formation of 2D perovskite phase.
Thank you very much for the question and Murali for the answer. Okay. Is there any other question or comment for Murali? I have few of them, but let me check if there is any other one in the chat. No. So could you please elaborate a bit on how you, I mean, you select your organic, let's say, dopants that you are putting in your perovskite? Is it like you're just try and see what it works, or there is a theory behind these additives, selecting them to work properly before the experiment is done? Are you doing any simulation, or how do you select them properly?
Yeah, sorry. Actually, the one motivation is actually the previous reports based on this organic blends. The first step was like this, like it is not like a particular motive to choose this one, but the reason to choose this C8BTBT especially is when it forms a film, when you make a film with C8BTBT, it tends to form layered morphology, which resembles like the two-dimensional structure. So we got a feeling like this kind of combination, either it would give a new replacement of these ligands, or it could give a separate, semiconducting channel within the material. So that was the initial motive. So it is not like some kind of big theory behind it. The main thing we choose is like this material is high mobility material and stable material as well as, and also it forms layered kind of morphology. So these are the reasons to choose this one. And then also I checked with various other non-layered materials, and though there is a little changes in the morphology, but which is not like the case what we have seen here. In this two-dimensional case, we have seen very neat uniform petal-like morphology, but with other non-layered kind of perovskite organic molecules are not giving such morphology. Only they are manipulating the grain sizes. Other than that, nothing much we have seen.
And my second question is, have you tried to use this strategy for other application rather than LEDs, for example, PV or transistor?
Yes, I haven't included in this presentation, but I checked the solar cell and laser as well as the photodetector. So these three also we checked, and all the cases it is working effectively.
For the photovoltaic device, what is the main reason for the improved efficiency? What is the figure of merit regarding the photovoltaic characteristics that is improving when you're applying this doping strategy?
So this is just like a guess, because the more studies we haven't done, but some initial studies, like one thing we checked the lifetime, PL lifetime. So the lifetimes are increasing for the blends basically. And second thing, the improved crystallinity might also one reason for the enhancement.
Yeah. So now I would like to ask you regarding the stability of your LED. So what type of stability test are you performing, and what is like, because for example, in solar cells, we have some protocols that we follow, and we can somehow predict even or accelerate and predict the lifetime of our devices in a very short period of time, but we can predict it for maybe what will happen in 20 years. What is there any such a protocol in LEDs, and how do you see how do you envision that you will be able to improve the stability of your LED?
Yeah, so the first thing should be optimized for the better charge balance. So that is the first important strategy. So we have seen there's a roll off when you see this performance here after certain voltages like 4 volts. We have seen there's a roll off even in the luminance after some 4 volts. The drop in uh, luminance. So this is because of imbalanced charge carriers. So that is one thing one needs to optimize. And also, as of now, the stabilities were not that great for the perovskite based light emitting diodes. The reasons are manifold. That because it's not only to do with the perovskite material and also various other layers. In our case, we suspect that we used the 2-pack material, and we suspect that with the time maybe their stability, we are suspecting about their stability because they process that a bit normal temperature. So if any temperature gradient can causes hampers the device performance. So these two reasons that we are actually seeing as of now. Yeah, as you can see, like it is not that much evolved as like photovoltaics for the time being, because the stabilities are pretty low.
And about the protocol, is it so to compare, for example, with another study, do you have like a systematic protocol that
Yes.
you use in LEDs?
Yes, you mean at what value you should able to
Yeah,
compare?
like is it stressed at high temperature, humidity, or do you keep constant and at
Yes,
current value, or what is the protocol?
the luminance basically. So the luminance, usually the majority of the reports are focusing on 100 candela per meter square, the luminance. So the stability they usually check at the 100 candela per meter square. At these are measured under the inside the glow box, but ideally it should be measured also outside in the regular ambient and humidity conditions. Yeah, so this is the standard thing, like majority of the people are using 100 candela per meter square as an initial one.
Okay, I can see another question in the chat from Miguel Anaya. So have you estimated the temperature in the device when you operate, let's say, at higher than 3 volts?
Yeah, that measurements were not done, but yeah, some of the people are working now in our group. So I think this is the only prediction. So we haven't estimated it.
And but for this one, can you explain why to the audience it is important to have this information?
You mean the temperature?
The temperature at high voltage. Can you explain?
Yeah. Because when we are particularly when we are measuring the stability, we are giving a constant bias. So with the induced, so the if the temperature dissipation is not properly done, with the time the temperature increases because of the internal resistance increases. So this is the reason to have this low stability. So one needs to have a strategy to have a good temperature dissipation, which means kind of a radiative cooling or some kind of strategies might help. Yeah, would that answer your question?
Yeah, I think so. And I see another question from Miguel again. Also, why do you see an increase in luminescence in the first few minutes? Is it bad injection, increased temperature, degradation?
Yes, this could be that we still have this doubt about it. It is actually showing for all the devices, and also we check the literature, and people are not talking much about it, but we suspect that the little improvement with the initial, increased temperature, maybe that could be the reason.
Okay, and I mean, just to give an idea to the audience, what is the target, the target stability
Okay.
in order to say that this kind of device is stable? And
ideally, it should be like few thousands of hours.
And what is let's say the acceptable loss it can have?
Okay, so we usually measure the T50. So at 100 initial luminance, so the time reaches, means the luminance reaches to its half value, should be at least 1000 hours. So it should be acceptable. Means when you extrapolate it or something like that.
Okay, so there is another comment. The field needs a lot still to have something close to acceptable, from Miguel.
What was the question?
No, there is a comment from Miguel Anaya. The field needs a lot still to have something close to acceptable. I think he's referring to the stability of the perovskite LEDs in general. And yeah, I think yeah, for market. Yes, so I think we can close here in case there is some time for more comments or questions to the speaker. If it's not the case, I would like to thank you again, Murali, for the presentation. It was a great pleasure and honor for us having you today, giving this presentation about a topic that looks very promising, especially for this type of materials. They have very interesting luminescent property. So I think Miguel is also here, so I will now give him the co-host permission.
Yeah, sure.
So, hello,
Perfect.
Miguel.
Hello.
How
Can
are
you hear me?
Yes,
Fine.
I can hear you. So I will start your introduction in 2 minutes, and then
Sure.
we can start your presentation.
Perfect. I was just wanted to mention that, I mean, Murali, nice results. I mean, we have time, right?
Yeah, so maybe I can unmute him, so if you want to have a discussion.
Yeah, because I mean, it's very nice. These self-assembled molecules are very complex. So because we have a lot of experience in using them for solar cells, and even like a tandem, like not only single junctions, but also tandem solar cells. But when trying to integrate them in LEDs, we found them very difficult. It's very nice. We even tried this MIO2 PAX VR with the VR termination with the roaming one, and we were not able to do it. So yeah, this is very nice. And what I was meaning, so when I was like commenting here in the channel in the chat that the field needs a lot to still to have something close to acceptable. I meant for the market. The stability of the LEDs that Murali was showing are like among the state of the art in the field yet, but we have still yet a lot of to do in the field.
Yeah.
But as far as I remember, also the organic LED starting with very poor stabilities, but they managed to do some researchers, and they managed to do some great improvements, and now we see organic LEDs everywhere. So maybe we have to wait a few years.
Yes, I mean, I think one of the main problems in perovskites, and I don't know, Murali, if you agree with this, is the ionic behavior. So they are not static. They are always, they have a transient behavior also in structurally, morphologically, etc. So you start having accumulation of stuff in the interfaces and also very deep valence bands, which make it difficult to inject the holes, which is to me the main problem in perovskites.
Yeah, it is quite possible. But what I could see when you were working with this kind of quasi two-dimensional perovskites, that problem should not be, much affecting, because these are like a kind of a quantum wells. But still, there is of course, a bulk systems as well also included.
What problem you say it is not a?
You mean the ion migration?
Yes, but I mean, you still have the organic the organic material in there. Like actually, you have a phenylethylammonium, right? And that's very volatile as well, and things.
Yeah, exactly. Yeah.
I think. I mean, I think there are a lot of questions for LED, like to understand what is going on in perovskite LEDs.
Yes.
Okay, so I think we can close
Thank you, Murali.
Murali's discussion.
Yes,
So
thank
please,
you.
Murali, send me your slides if possible. We put Costas in CC.
So I'll send to your mail address. Okay.
Yeah, fine. Okay,
Okay,
so
thank you
very much, Murali. Great. So now I will start with a short introduction about Dr. Miguel Anaya. So he is the recipient of the Royal Academy of Engineering Research Fellow at the Department of Chemical Engineering and Biotechnology and a Research Fellow at Darwin College at the University of Cambridge. He graduated from the Autonomous University of Madrid in 2012 with a bachelor and master's in physics with first-class honors, and he obtained a second master in material science 2013 at the University of Seville, again with first-class honors. He completed his PhD at the Spanish National Research Council 2018 with a recognition from the Spanish Royal Society of Physics as the best thesis in experimental physics. Miguel currently leads a team focused on the modeling, fabrication, and characterization of perovskite-based devices at the optoelectronic material and device spectroscopy group. And for this work that he is currently doing, he has received a SPA scholarship, a EMRS Student Award, Best Young Investigator 2016 by City Hall of Seville, and he has been distinguished as the Emerging Investigator of 2021 by the Royal Society of Chemistry. And in general, he has received, even though he's at his early stage of his career, he has already raised more than 1.5 million pounds funding. So it is a great pleasure and honor for us for this intensive course to have such a distinguished speaker like Miguel Anaya. And that's now I will give you, Miguel, the floor to start your presentation. I can see you have already shared your screen. The slides are working properly. Thank you very much.
Perfect. Thank you very much, George. Very long introduction. Thank you very much, and thank you for inviting me to give here this presentation. I have prepared it in a way in which I will try to make it more accessible. I don't know how familiar is the audience with the topic and all these microscopic techniques I'm going to show. So I'm also like happy to stop if you have questions at a particular moment. Just interrupt me. I'm happy to answer. Thanks, George, and all the organizers for accepting me here, and also like I mean, I just wanted to say that the lineup of speakers is great. I would have liked to see more women, but it is very good to see such a good lineup of speakers with different approaches, different applications, and I think the people that have registered, they will have a very good breadth of what is going on in perovskites. What I'm going to explain today is, or what I'm going to discuss today is about this nanoscale landscape in Halide perovskites, which we have found, or we believe it is behind or the working principles that govern how these materials or these devices perform in the macro scale afterwards. Okay. let's see if I can. Okay, perfect. I'm going to introduce the topic very broadly because I'm not sure what you have been listening to in the last few days and including today. These perovskites are not new. These perovskites, these halide perovskites were first described in the late 50s and then in the late 70s, as you can see here in this German paper. Structurally, and so they are known materials that receive their name because of the way in which they assemble in 3D dimensions. But it was only in 2009 when the team of Miyazaki in Japan proposed them to work as a die in a dye sensitized solar cell configuration. Okay, showing devices that were around 3% efficient. Okay. It was later, in like a couple of years later, I think in 2012, as you can see here in these panels on the right, when teams from South Korea and EPFL and again the team of Miyazaki plus Henry Snaith in Oxford that demonstrated or employed these perovskites more like in a solid state configuration, able to reach or to surpass 10% efficiency, or even reaching 12% efficiency at that time in the solar cell. That was a breakthrough, and that was the explosion of the field because people, the field understood that they are not just a dye or an absorber of light, but they can also generate charge current and conduct not only electrons but also holes and have like a good devices even in planar structures. Okay. These perovskites are part of the third generation photovoltaic technology. First generation, we have crystalline silicon. Then after, a couple of decades after, like amorphous silicon, CIGS, and some others appear as the second generation. And then the third generation with dye sensitized solar cells, organic solar cells, which are more based on thin film technologies that you can deposit very easily, usually, or like even compatible with flexible substrates. And then in 2009, perovskites appeared. I'm just showing this this top let's say line because I believe that perovskites have been able to evolve so fast because of a couple of two main reasons. First is that they are easy to prepare and their properties are very interesting, as you will see in a minute. But also because there was a lot of knowledge already in the scientific scenario to bring to the perovskite field from the dye sensitized solar cells and organics. And we are not only using it for solar cells, but also for LEDs, because you have seen from the previous talk that we are most of the hole and electron injector layers in perovskite LEDs are also based on, or are basically a heritage of what was done in the past in organic LEDs. As I say, they have had a meteoric rise in efficiency in the last decade. From 2009, where we had in the Miyazaki's paper 3-point-something efficiency, up to go above 25%, almost reaching 26% nowadays, which is very close to the efficiencies of crystalline silicon or silicon solar cells, which is a much more well-established technology in the market, even with decades of developments. Okay, and you can see that the rise of perovskites has been a super sharp in comparison to the more asymptotic behavior of the evolution of silicon solar cell efficiency. As I say, this efficiency, this rise in efficiency is partially because of the knowledge we have from other technologies, other similar technologies, but also because they are very cost effective, while easy to prepare, showing very good optoelectronic performance. Okay. So these perovskites, just to remind everyone, received their name because of the 3D structure in which they arrange the atoms in the space, with a larger cation in the void left by each 8 octahedra. As you can see here in purple, this can be usually an organic material, methylammonium, or even formamidinium, or if you wanted to have pure or fully inorganic perovskites, it can be cesium. Then in the center of the octahedras, of the octahedra, we have usually in the 95% of the cases lead, a divalent metal, which is lead, but also we can have tin if we wanted to move or to shift the absorption onset or the emission towards the infrared, which is good for different applications, including tandem solar cells. But I'm going to focus on pure lead perovskites in this talk. And then what makes them truly unique in terms of if because there are many types of perovskites or for different applications. These halide perovskites, they receive their name because or the differentiating factor is that they have a halide in the vertices. Okay, so usually iodine, but also we can have bromine if we want to blue shift the band gap, or even chlorine if we want to go even farther to the blue. This is all this chemical landscape is very important because we can combine mix different cations, A-side cations or X-side halide to stabilize the structure, to optimize their band gap for photovoltaic or LED applications if we want it, or we can even make them more like a, let's say, optimum in terms of the Shockley-Quasar limit that I'm pretty sure someone has already introduced yesterday. On top of this, if we start playing with larger cations, we can start distorting this 3D perovskite structure. And for example, adding like a particular, like for example, ferritinammonium iodide or bromine cations, like the ones that were discussed in the previous presentation, we can start splitting or separating the octahedral sheets to obtain sort of 2D perovskites. They are not truly 2D materials because we always have, or they are not like exactly the same that what we have in standard 2D materials in the 2D scenario, because you have always you need the organic to stabilize the structure, so you don't have a free like standing free octahedral sheet. You always need the organics, but you can obtain like the quantum well let's say effect of splitting these octahedra in different numbers of layers. Okay, so n equal 1 will give like a very blue shifted or very confined let's say excitonic behavior that would shift the band gap towards the blue, like here. N equal 2 will have also like some confinement, but less than n equal 1, and so on. Okay. We can even also like prepare these materials in colloidal quantum dots in a colloidal quantum dot way. So using the ligands to fabricate the spheres or cubes, because these perovskites like have a preferential growth in the shape of cubes. Again, to have quantum confinement, but not in the 2D dimensions with platelets, let's say, but now more like in 3D confinement, to shift also towards the blue the spectrum. And I wanted to show this because I want to remind again like that adding bromine, because it is going to be very important later on in the talk, adding bromine to the compositions of the perovskites blue shifts the absorption onset or the emission of these perovskites. Okay, that's very important. These are perovskites. These are materials that we can synthesize easily. We just need to synthesize precursors in the laboratory, and we can deposit them by vacuum deposition, but usually the laboratories prefer to do it by solution process in spin coating, via spin coating, because it is cheaper and it allows you to screen a lot of conditions very fast. And that's one of the reasons behind the fact that these perovskites, the perovskite field or the solar cells have evolved so rapidly. However, this let's say way of growing these materials at mild conditions, because we don't need to synthesize them more at higher than 100 degrees, which makes them compatible with flexible substrates, cause this type of heterogeneities at the nanoscale. Okay, as you can see here, and I'm pretty sure that everyone that is working in perovskites here can recognize this type of scanning electron microscopy image, in which you can see this grainy structure of this typical grainy structure that the perovskite arranges upon the formation, upon the annealing of the film. And this is a result of the way in which we process them, because we just drop cast a solution in a substrate, spin coat, and everything self-assembled in a sort of messy way, but it works very fine. And this is going to be the main question I will try to answer in this talk. Interestingly, of course, the previous properties wouldn't be nothing if we didn't have very good optoelectronic properties. So they absorb light very efficiently. They they saw the 3D perovskites have a low exciton by energy, so you can dissociate electrons and holes very efficiently that can travel long distances, enough to be extracted at the contacts of a device. And they also saw a high efficient radiative recombination, which is very important for LEDs, but also for solar cells. Because if all the recombination that happens in the solar cell is radiative, it means that we don't have non-radiative losses, which are the ones that we would like to avoid, okay? Because radiative losses, due to thermodynamics, we cannot get rid of them completely, okay? One of the most important, actually the crucial question that I want to discuss today is the fact that these perovskites, even though they are messy and they in the nanoscale and in the macroscale we can measure like a sort of a high density of defects, they are still perform very well. And this is very in contrast with what we have learned from textbooks in our bachelor's. We have been told that to have a good optoelectronic device based on crystalline silicon or gallium gallium arsenide or even gallium nitride LEDs, we need them to be very pristine, very defect free, okay? Because a very isolated defect can be extremely detrimental for the device performance. In perovskites, of course, they are detrimental. We would like to get rid of all the defects, but they are there, and still the perovskite performs well. So you have seen before that we are reaching 26% efficiencies in perovskite solar cells and above 20% external quantum efficiencies in LEDs, which means that something is going on there to avoid the presence of these effects, or like to overcome the ubiquitous presence in the perovskite. As you can see here, they are like materials that have these grainy structures with full of grains, grain boundaries that, of course, they are inducing defects, as you will see in a minute. So this versatility, low cost, unique optoelectronics is what make them unique for solar cells, that we can have flexible solar cells. Probably yesterday someone was told explaining those. We can tune the bandgap of the material, but also due to their thin film properties, we can combine with photonic structures to have like a colorful perovskite solar cells, which are very important for building interactive photovoltaics. We can combine them with other perovskites or other type of photovoltaic systems to have tandem solar cells, which are important to surpass the theoretical ceilings in terms of the Shockley-Quasar limit for single junction devices. They have like good emission, which make them interesting for LEDs, as you just have seen. And something we are investigating also very actively in the group is that they are also good for X-ray detection, because and high energy radiation in general, because they are comprised of very heavy atoms like lead, and thus they can stop this high energy radiation efficiently, in contrast to other type of semiconductors like organic ones, okay, which are actually very light. But again, my focus will be trying to understand the why these perovskites are defective, but still perform well, okay? And again, we believe and we know that this defective character is related to the way in which these materials grow, because we employ these mild conditions, solution process, annealing at low temperature, that give rise to heterogeneities in morphology, as you can see here in this picture, at different length scales. So you can start with heterogeneities in the long range, like in tens of microns, in which a lot of people, and if you have looked at the samples in an optical microscope, you will probably see wrinkly structures like you can see in this map. If you zoom in to the, let's say, micron scale with an scanning electron microscope, you can see these grain structures I was explained before, with a lot of grain boundaries, probably sources of defects, with lead iodide also, or in principle lead iodide also shining a lot, being like resolved as very bright dots due to the presence of a lot of lead in those images. And even if we zoom in even more with, for example, a transmission electron microscope, we can observe that in each grain we can have like subgrain heterogeneities. Okay, and here you can see these lines that go across the grain, which are maybe like due to some crystallographic differences or torsions or even twins. Okay. So this means that if we don't look at these materials carefully at the nanoscale, we can miss a lot of information. And this is something that was first discussed in 2015 in this seminal paper by the colleagues in Science, where we first correlated a scantron microscope image with a confocal image, okay, with measuring the photoluminescence. At the back of this map, you can see the grainy structure, scanning electron microscope, SEM, and then in the color map, what they represented is the photoluminescence intensity measured with a confocal microscope. Okay, and what you can see is that there are grains that are very bright, which is great because more emissive, better relative recombination, or like more emission means lower non-relative recombination, which is what we want to avoid in a solar cell. So bright is good for solar cells, but in contrast, there are other grains that are extremely dark. Okay, as you can see here at in the one I'm pointing now. This means that these materials are not as good as they could, and we have two questions. Like first is, why are they performing well in spite of having very dark grains? Which in other type of semiconductors like silicon will be completely a complete disaster for the solar cell. And second, can we avoid the presence of these very dark grains, or like can we make all the film as bright as possible or as good as possible in terms of optoelectronic photophysical performance to then translate them in better devices? I'm going to try to answer today the first question, like the fact that we have like this coexistence of good and bad areas in the perovskite films, but still the perovskite is performing well. Okay, so the first part of the talk will be about how, or let's say more like about results. How do we image the presence of these defects? Because you have seen, what you see in this map is, let's say, the fingerprint of the existence of defects, but which is the like low PL. But where are these defects? That's something that is complex to do, and we have some techniques I'm going to show today. One to try to resolve with better resolution where they are. The second thing I want to note here is that I'm going to focus in a state-of-the-art perovskite material, which is in the one that we focus in the group, which is triple cation perovskite, which is basically a complex alloy of cesium, formamidinium, and methylammonium in the A-side cation, which allows us to stabilize the perovskite quite well, and also like a mixture of iodine and bromine, which has the like two sides of a purpose. One is again stabilizing it even better, but also the presence of bromine, as you will see in my talk, is crucial to achieve maximized performance. Okay. So the way in which these defects can be directly imaged and not just a result of the photoluminescence, but if the way in which we know that we can detect this or like a map or image these defects is by, for example, photoemission electron microscopy. Okay, PEM, PEEM. And this is something that the group of science strands in which I have been working the last few years have performed in collaboration with the group of Kesaftani and the University of Okinawa. They are the ones performing this type of microscopy. And basically what you have is a sort of high energy photons excitation. When I say high energy is ultraviolet photons in comparison to optical photons, like for example 4.65 electron volts and 6.2 electron volts that are able to excite electrons from the valence band and the band gap of the perovskite, extract them, and then we measure the kinetic energy. That kinetic energy of those electrons can be measured with a microscope. Okay. The interesting thing here is that we can achieve much better resolution than with an optical microscope, even though we excite with with let's say ultraviolet photons. What we measure are electrons, so we can achieve quite good resolutions. Okay. And as I say, we excite electrons from the valence band or the band gap, sorry. And what we measure is the kinetic energy of those electrons. And with knowing the energy that we provided to the system, we can extract exactly from where they are coming from the sample. Okay, or like in terms of energy. Especially we know because of the way in which we scan the sample. Okay, so the interesting thing is that for example, this is basically what you can obtain in the map. In every point of the map is this type of image, which is beam signal, and then the energy of the photon that you are receiving. And what you see is that we have a peak of electrons that you are receiving, a peak of detected electrons for those that are launched from the valence band. Of course, if you are you are exciting the sample, most of the electrons that you're exciting are in the valence band, of course, because is the most populating band. And interesting thing is that when we excite with a ultraviolet laser, which is of lower energy, that only, let's say, monitors or can extract electrons from the band gap, we still see a tail in receiving electrons in the camera. Okay, and this is very interesting because this means that there are in some areas there are electrons in some gap states, so there are defects within the band gap. Okay, and this is basically what you can see in the right hand side map. In the black and white map, what you see is the image obtained by with a 6.2 electron volt excitation. So electrons are proportional, or the electrons that you receive are proportional to the, let's say, the amount of material, sort of. So you see brighter, like brighter image when you have like a more perovskite. That's why you can resolve the grainy structure more or less. And when you excite with these like lower energy photons, what you extract or what you monitor are the electrons that are present within the band gap. So those that are sitting on traps in the film. Okay, and this is very interesting because you can see that there are these traps are located in very particular points, and they are quite ubiquitous. So they are not the density of this defect is not incredible or like incredibly high, but they are everywhere. You don't find areas that are extremely pristine. If you map a large area, you see these defects, and that's a very interesting thing because this means that these traps in perovskites are ubiquitous and they are there as we predicted. So what you see here in this image now is a correlation, or what I'm going to show is a correlation of the presence of these traps that we can detect by beam with the effect that they have on the photoluminescence of the film, which is measured again with a confocal microscope. And here you can see that the difference in intensity of the photoluminescence of this of a perovskite film, and when we overlap the presence of defects, you can see that those fall perfectly in areas in which the photoluminescence is dark. Okay, the photoluminescence is low. Again, confirming that presence of defects give rise to low performance. Okay, which is what we knew, but this is the direct visualization of traps giving rise to low PL performance. Here I just want to show that these defects that we were observing before are sitting preferentially in between grains, so at the grain boundaries. And again, on the right hand side image, what you can see is that is an overlay between the PIM signal of the defect, so the blue one, with a correlation with the AFM, which can give us like very good spatial resolution. And again, you can see that most of defects are like in areas that are grain boundaries. Okay, so we have this first part of the talk. I hope I have convinced you that the existence of this defect is ubiquitous in the perovskite film, and that these defects are preferentially located at the grain boundaries. There is a lot of literature and discussing which is the structural or compositional origin of those defects, but I'm not going to go through it for the sake of time. But if you have questions or you want to know about literature, I can pass you some papers about that. Now that we know that we have demonstrated that these defects exist, can be visualized, and they are everywhere, let's say, the question is why the perovskite still performs so well. So in order to answer that question, we have developed a multimodal, like a suite of multimodal microscopy techniques in which we use hyperspectrum optical microscopy, transient absorption microscopy, and then X-ray microscopy. So all photons, let's say microscopies based on photons, but with different energies, to try to answer this question. Okay, so the first one is this hyperspectral microscopy technique, optical microscopy technique, in which we basically illuminate a wide field sample, and we obtain images in a camera that we feel like monochromatic images in a camera, in which we obtain like different frames for different wavelengths, as you can see here on the maps that I'm now pointing, in which of course we have let's say heterogeneity in the response that we get in the spectral response that we get spatially, but doing some let's say processing in terms of the analysis, we can chop the maps and reorganize them to collect like let's say frames in which we have a single wavelength map. Okay. And then we have these frames that convert form the complete spectrum of the photoluminescence, reflectance, or transmittance, as you will see in a minute. Probably this is complex. I'm showing this slide for you to understand it better. Basically, on the left, I'm showing the type of map that we can collect at every wavelength, and these are cesium-lead bromide microcubes emitting at around 540 nanometers. So this is the photoluminescence on the left, in which you can see every frame is for different wavelengths of collection. In the center, you see, let's say, a static picture at the peak of emission, and then a point that is scanning across one of the cubes. And then on the right-hand side image you can see the spectral evolution of the photoluminescence of that particular point, of that particular cube at the points that I am scanning. Okay, so you can see that the intensity of the photoluminescence is changing, but not only that, also the spectral shape. Okay, and that's very important because we will see later that in films the spectral shape of the photoluminescence is dictating a lot, or is telling us a lot about the working principles of these perovskites. This wide field imaging microscopic technique is very good for our purposes because we minimize the diffusion effects. So we illuminate all the samples at the full region of interest at the same time. So we don't have let's say gradients of charge carriers that induce the diffusion to preferential locations. So everything is excited, let's say, with the same density of photons. It allows us to acquire fast and low dose. So we can reach like 1 sun equivalent illumination, which is what is interesting for us. We don't want to go to very high illumination conditions, which are not relevant for solar cells, for example. And even they are low dose and the signal in principle should be weak. We can acquire these images quite fast. So basically we can collect this type of spectra in a couple of minutes, okay? Which is good because these materials, as you know, can degrade over time. This wide field hyperspectral microscopy has been, the development of this microscopic technique has been led in our laboratory by a brilliant PhD student, Kyle Fronag, which is graduating very soon. And the particular thing that we can perform with it, or let's say the added value that we have in the group, or we have developed in the last 3 years now, is that we can measure absolute photoluminescence, reflectance, and transmittance spectra. And this is very important because with this, we can extract very unique, very important values or proxies, metrics, which are proxies for what one can expect in a solar cell, okay, in terms of performance. So we can extract quasi-Fermi level splitting maps, photoluminescence quantum efficiency maps, and urban energy maps, okay, and I'm going to explain them in the next slides. This is just the configuration of our microscope, in which we can measure full devices if we want. In this talk, I'm focusing only on devices on devices that are measured, let's say, at open circuit, devices not in operando conditions, so just at open circuit voltage. We can now do also like a operando microscopic measurements, but that's another story not for today. This is just the type of maps that we can collect: reflectance, transmittance, which are in which you can see that we can have a diffraction limited resolution of around 300 to 400 nanometers, but still we can see differences in reflectance and transmittance for different grains, and even the effect that the grain boundary has on those metrics. And of course, if now we reshape this reflectance and transmittance in terms of absorptance, following the standard equation, we can get the typical absorption profiles that one can measure in a perovskite material at the macro scale, but we can obtain them at the nanoscale. Okay, and you can see that there are differences in like spectral differences in the absorption depending on where you are measuring the sample. But the most important thing is that no matter where, we always have this very sharp absorption onset, which is very typical in these perovskites. Okay. Also very important is that if we now integrate or like average the absorptance or the transmittance or the reflectance that we obtain in one of these maps in let's say 100 by 100 microns, what the spectra that we get are exactly the same ones that we measure in a standard UV spectrophotometer that you can have in your labs, okay? Now, if we have the absorptance, we can divide, let's say, the absolute photoluminescence, spectra that we obtain if we measure photoluminescence by this absorption, and obtain what we call photoluminescence quantum efficiency, which is a very important metric because it is telling you directly how many photons that from the ones that you're absorbing, the sample, the perovskite, is converting into emitted photons, okay? Which is basically telling us how good is our sample in terms of radiative recognition. Okay, this is probably the first map. At what I'm showing here in greenish colors is probably the first photoluminescence quantum efficiency map at the nanoscale that you have seen, in which the spectral response of the photoluminescence can be also resolved at the same time, okay? So you can see that we have photoluminescence quantum efficiency oscillating from 4 to 6% depending on the point in which we focus our attention in the sample, but also we have differences in intensity in the photoluminescence and changes in the shape, for example, with shoulders appearing in the red tail of the photoluminescence spectrum, okay? Which is, keep that in mind because that's very important for the rest of the slides. Again, if we now integrate the photoluminescence quantum yield, quantum efficiency from this map for the whole map, what we obtain as a result is around 5.5%, which is exactly the same value that we get in an integrating sphere at the macro scale, okay? Again, validating the approach that we are performing. As I was saying before, we can also obtain quasi-Fermi splitting maps. This is very important metric because it's giving us like an upper bound value for the expected open circuit voltage that one can have when operating the device. Okay, that's why quasi-Fermi splitting maps are attracting a lot of attention in the field now, because it's a direct or can be directly translated in what you could potentially achieve in a solar cell. It's telling us how the material or the different interfaces are also affecting the material. And basically, we can obtain it because we can measure as I was saying before, the absolute value, values of the photoluminescence intensity and the absorption. And basically, here what you have is the generalized Planck law, in which we have the photon density of states, the absorption which we approach to be constant, and then of course a Bose-Einstein occupation function that we reshape as a Boltzmann distribution, okay, for simplicity. And then you can extract, or basically taking the logarithm at both sides of this generalized Planck law, we can extract the quasi-Fermi splitting value from here, okay? And this is what you can see here in a standard perovskite film with quasi-Fermi splitting values oscillating between, let's say, 0.98 to 1.2, which are values that one can expect in a not very good solar cell, but perovskite solar cell, but still close to them. Okay, and then when we translate them, this particular material in a solar cell, we observe that the open circuit voltage that we get is around 1%, 1 volt. Okay. And in the same way, or really similar way, if we reshape the generalized Planck law in terms for the absorption, and we do like some approaches to reshape the absorptance as a function of the absorption coefficient, we can extract the Urbach energy, okay, from the low energy tail of the photoluminescence. And this Urbach energy is a very important proxy. Again, we can extract it doing some numerical calculations, because we just need to calculate the inverse of the slope of this function to extract alpha, Urbach energy from this denominator in the alpha exponent. Okay, and this Urbach energy is very important because it's giving us a proxy for the electronic disorder in the sample. So basically, the higher the Urbach energy that we calculate, the higher the electronic disorder in the sample, which is typically bad. Okay, what you want to have is like a very good electronic order, so lower Urbach energies. And this is something that you can start observing, or this type of trend is something that you can start observing if we correlate different metrics. For example, if we have now the photoluminescence quantum efficiency map on the top of one of these triple cation samples, the Urbach energy map at the bottom of one of these triple cation samples, if we correlate them, what you can see is that areas showing low photoluminescence quantum efficiency, so areas that are bad in terms of optoelectronic performance, they always show or tend to have higher Urbach energy, okay? So higher electronic disorder. Interestingly, the areas that in which we show higher PLQE, so the areas that are good, always or tend to show in our maps, in these triple cation samples, low energy solder, okay? So a solder in the red region of the photoluminescence. And this is very important. And the key takeaway message of this slide, because which is that brighter areas have lower Urbach energy plus a red shifted emission solder. This is very crucial because red solder in the emission will mean, in principle, as you can see in this plot, that and let me change. Okay. Okay. As you can see in this plot, the red shifted band gaps in perovskites tend to mean that you have more iodine in the composition. Okay. In other words, if you have blue shifted emission, it means that you have more bromine. Okay. So in principle, if okay, in principle, here this red solder would mean that we have more iodine, okay, in the sample. But you will see that it is not the case, and that was very puzzled us a lot. Okay, so in order to understand, or in order to confirm the composition of our samples in the nanoscale, we need to take advantage of synchrotron radiation. Synchrotron radiation, which is basically you have electrons here that are accelerated very fast in this circle, in the synchrotron, and they emit very high energy photons. In our case, in this case, depending on the how fast these electrons turn, you have different X-ray energies. In this case, we have a high energy X-rays with very high quality X-rays that we can in 150 meters. In our case, we can let's say focus the beam and use it to map our perovskite film at the nanoscale, okay, with a resolution of 50 by 50 nanometers, as you will see in the next slide. The X-ray, these hard X-rays can penetrate the sample, and in transmission we can collect diffraction patterns or diffraction spots for every single point. We can scan it, and in reflection we obtain X-ray fluorescence. Okay, X-ray fluorescence, which is depends on the composition of the sample. Okay, I'm going to delete this, change again. So yes, we make use to do this. We go to the diamond light source, which is the synchrotron in the United Kingdom, and what we can measure is nano X-ray diffraction and nano X-ray fluorescence. Okay, with X-ray diffraction we get structural information, as you can see in this panel in the center, and with fluorescence we obtain composition information, as I was telling you before. Okay, and again, like it happened with the optical microscope, here in this X-ray microscope we can scan across the sample and check heterogeneities. I'm not going to focus on diffraction. I'm just going to focus on fluorescence because it is the important thing for this work. And what we can do now is to correlate one point by point. So we can take the images that we had in the optical microscope to do like a to have the let's say the quasi-Fermi plating or the photoluminescence quantum yield, etc., and correlate it directly with the composition of the sample. Okay, I'm going to show just here how we can translate this let's say X-ray fluorescence spectra into maps. Okay, which is what you can see in the right hand side part of the slide. The B panel B is just the signal for gold, which is what we use to correlate the different, like to find the same area in the sample. So we have golds that have like a very particular shape, and we can find, we map them in the optical microscope, and then we go to the synchrotron and find them and map exactly the same area. Okay, that's how we can align and know that we are measuring same areas, and we can, let's say, correlate point by point different techniques. And basically what you can see is that we have heterogeneities of lead, iodine, which are we have found that they are directly related to the thickness of the sample, variations in thickness. But what we have found is that bromine, and this is something I'm not going to discuss because I don't have time, but bromine is basically related, is the let's say the one that is not, is an element that is not related to anything the thickness. Okay, so now if we see that this variation in knowing that this variation in bromine is the one that dictates or have like a more heterogeneities, real heterogeneities in the sample, we can extract areas that are high content in bromine. These are the ones on the top panel in blue. Okay, the 20% areas with more bromine in the sample, and correlate them with Urbach energy. And what you can see is that the areas with more bromine anti-correlate with Urbach energy, which means that more like better electronic areas in terms of electronic disorder correlate have more bromine, okay, in the composition, and the other way around, areas with less bromine here in white are correlated with areas with more electronic disorder. Okay, and this is counter intuitive, because if you remember from what I was saying before in the optical microscopic technique, areas with better Urbach energy, so lower Urbach energy with better order, were showing better PLQE, of course, but they were showing an emission in the red, which is contradictory with what I was saying, because now we see that they are more bromine content. Okay, so better performance, red emission, but more bromine. That's very puzzling. Okay, so that was something that took us like several months to try to understand. Brighter areas that are bromine rich but have red shifted emission solder. So in order to understand what is going on there, and I'm going to go fast through this because this is a little bit it's a complex technique, but basically we established a collaboration with Aksai Rao group in Cambridge as well to perform transient absorption microscopy, which is a pan-probe technique that allows us to get microscopic insight into the dynamics of the charge carriers in the first picoseconds upon excitation. Okay, so basically what we are going to do now is a full correlation between photoluminescence, composition, and then dynamics, or let's say transit dynamics of these charge carriers in the first picoseconds after excitation. Okay, so now what you see here on the top image is a line scan of what I was discussing before. Bromine rich areas are highlighted in this blue rectangle, and so high PL, like a good like photoluminescence in black here, and then poor bromine areas that are highlighted by this gray rectangle, so low PL. Okay, now we correlate this line scan with the time evolution of the ground state bleaching energy. Okay, and what you can see is that in the bromine rich areas, the ground state bleaching energy starts, let's say, at high energy, energies like 1.66, and then shifts rapidly in just 500 picoseconds to energies around 1.63 electron volts. Okay, something that is in very contrast to what happens in bromine poor areas, in which the ground state bleaching energy is constant and doesn't move at all during in terms of energy upon like after this half a nanosecond. And very interestingly, if we take a more like we focus more the attention on what is going on in terms of the energy evolution with time, we just take snapshots at 10 picoseconds, 250 picoseconds, and 500 picoseconds. You can see that the ground state bleaching energy again here then shifts towards the lower lower energies for the high bromine content areas, but they do it without losing let's say signal. Okay, whereas in the areas in which we have poor bromine content, the bleaching happens and losing like the ground state bleaching energy doesn't shift but loses signal. Okay, this means that the transfer that happens in the bromine rich areas is very efficient, and is basically what we believe is behind the fact that the defect tolerance in these samples. And I'm going to try to okay, 1 second, to draw something here if I can. Okay, so basically what we have is a competition between the chemical landscape and the electronic landscape. Okay, so we have samples, as I have been showing in the presentation, with ubiquitous traps. So there are traps everywhere in the sample, which is what you can see in this schematic at the bottom left, but I'm going to try to plot it better. We have traps everywhere in the sample. Okay. And what happens in the bromine rich areas, for example, in this bromine rich area, is that we manage to pull away charge carriers from these traps very quickly and make them recombining in areas in which we have very emissive, very high radiative recombination rates, which is something that in the poor bromine areas doesn't happen. So in the poor areas, some charge carriers can fall into those traps and they are low emissive. Okay. And this is basically what we conclude in this slide, that the bromine-rich regions have nanoscale iodine-rich domains with high photoluminescence quantum efficiency and low Urbach energy, which are formed during the synthesis of the samples because of this messy structure. These carriers funnel into these domains very quickly, and they are the ones that are responsible for avoiding these traps. Okay, whereas bromine-poor regions have no such funneling effects that allow us to avoid those traps. And this is basically what we have published almost a year ago now, and you can read more in this Nature Nanotechnology paper in which we got the cover of in the journal, and in which we try to represent this funneling effect by this sort of black holes that we have represented here. Anyway, now what we are doing in the group, and I'm not going to go through it because I don't have time, but basically what we are doing now in the group is, instead of measuring the samples at open circuit voltage, like just films, we are measuring devices at operando. Okay, so we apply a bias in the device, and we extract all these type of metrics, quasi-Fermi level splitting, Urbach energy, extraction efficiencies, while applying a bias. And I hope I have convinced you of the importance of taking a look at these perovskite samples at the nanoscale as well as possible, because in the nanoscale is where we have the answers to the way in which these perovskites perform, and why they are defective but still performing well, why they have ubiquitous side effects everywhere, but we can manage to avoid them by serendipitously forming funneling or charge carrier funneling areas from bromine rich to iodine clusters that are very high performing. And with this, I would like to thank all my group, the group of Sam Strangs, with which I have been working in the last 4 years, especially Khalid Frona, Tiernan Doherty, and Stuart McPherson, which are the ones that have been performing these measurements. All the sponsors, especially the Royal Academy of Engineering, which is funding me, and you for your attention. I'm happy to answer any question.
Thank you. Thank you very much, Miguel, for the very nice and detailed presentation. Now I will give the floor to the audience for questions and comments. I can see the first one in the chat from Preet Wiz, and the comment is the following. The question is the following: when making the triple cation perovskite solution, the sequence of adding solutions can change the final stoichiometry. Adding 0.05 cesium iodide or 5% cesium iodide in 95% formamidinium lead iodide, and then adding methylammonium lead bromide to this mixture solution, or mixing formamidinium lead iodide and methylammonium lead bromide first, and then adding 5% cesium iodide to this double cation mixture, or 3, adding all 3 85% formamidinium lead iodide, 5% cesium iodide, and 15% methylammonium lead bromide separately in one mixture. How do you add cesium iodide, formamidinium lead iodide, and methylammonium lead bromide to get the least defects in the film? That's
a good question, and I don't have the answer right now. I need to go through the notes because I was not preparing the samples. I was more in charge of the optical, like the microscopic techniques and the analysis. I can check, but to be fair, we are not looking here for. I mean, what I was trying to discuss here is why the materials perform well, even though you have defects everywhere. Okay. Now, what we can do with this technique, as I was saying sometime in my talk, is or with these approaches, is to try to identify the way to avoid those traps or to minimize those traps, which we have seen that they are quite benign, but we still want them we still want to get rid of them completely. Okay. The point is that I don't think we have much different in terms of defect density depending on how we mix the precursors. I have to check that, but I don't think we have like we see much difference. But I have to say the methods of our paper to see how we make them, because to be fair, but that was not the focus of the paper or the work. We were interested in understanding or like observing the traps, understanding that they are ubiquitous, where they are, and why, in despite of having them everywhere in the sample is still, or let's say the perovskite solar cell is still performing quite well.
Maybe if you could type in the chat the link of this publication, and
Yes.
this person can go and check how you prepared your samples.
I mean, it's the one that you can see here. It's the citation you can see in this slide.
Okay, great.
But
So
I can.
then I can move to the next one, which is from Mustafa, and the question is the following. Thanks. When fabricating a film from the colloidal solution, which has OA and OAM as ligands, how to rid of maybe how to get rid of the excess, the ligand excess, since we finally get a wet film, even if we do annealing, since the boiling point of the ligand combination is around 360 degrees C. Also, washing with toluene, hexane, acetone almost cause aggregation. What is the tip here?
So I'm reading the question again, sorry. So I don't know. This is something again. It's about synthesis of colloidal quantum dots, as I see here from perovskites, which is not the focus of this work. I'm not sure if this question was for the previous speaker, but from what I know, you need to be very careful about how you wash the nanoparticles, because if you let's say degrade or like wash them too much, you can start not only getting rid of the ligands in excess, you can also start like the attaching ligands from the surface of the perovskite nanocrystal, and then those can start degrading or merging between them, and then you lose, let's say, the monodispersed character of the colloidal suspension. But again, I'm not sure. This is not very related to what I was discussing, I think.
Okay, thanks for the answer. We can move to the next one, which is from Temur Maksudov. Thank you for the interesting talk. With such high energy photons from synchrotron experiment, will the perovskite field be damaged? This is the
That's a very good question. Yeah, that's a very good question. So the person in the Temur is asking if with the X-ray radiation we can damage the perovskite. Yes, we can. But you need to find, so I'm just putting the slide about X-ray. Yes, you can damage the sample, but you need to find the conditions that are okay. So basically, we have been working like for around 1 or 2 years in trying to find which are the doses of X-rays that we can employ to get reliable data. Okay. When I say reliable, is that we tend to find that so to make sure that they are reliable, we scan twice the same area, and we obtain that the sample is not severely damaged, okay, with X-rays. And that tells us that the doses that we are employing are good enough or are low enough to not induce any chemical change in the material, okay. This is the high intensity X-rays. That's something that is clear. But just I think the integration time per point is I don't remember for these particular maps, but maybe like fraction of seconds. Okay, so it's very fast what we do. So the sample is not super exposed to the X-rays. If so, maybe, and then the person in the audience is saying that if they are damaged, maybe the bromine-rich areas are more pronounced from the damage of the beam. Yes, again, so that's what we have been exploring also. Like there are a couple of papers now from the group as well discussing X-ray and electron beam damage in perovskite films. We don't see that effect in the, we don't see the formation of bromine or the degradation of bromine more pronounced upon the excitation or upon exposure to these X-ray energies. Okay, at least with the protocols that we have established. Okay.
Thank you very much for Timur for the question and Miguel for the answer. I don't see any other question. If you would like to ask any question, we can raise your virtual hand or type it here. I have one. So have you, Miguel, have you checked the environmental, I mean, contribution when you are doing this type of measurements? Like, for example, if you have checked the effect of humidity, temperature, or combination of this, or how do you perform your measurements to make sure that the samples are not degraded during the measurement from the environmental impact?
That's like an extremely good question. So first thing is that we don't see very important changes in these perovskite films. These are triple cations, so they are quite stable under different stresses. We don't see very important changes when we expose them to air for the time in which we perform the measurement. What we make sure of, like, again, it's a little bit related to the previous question. We make sure that if we do like twice the same measurement, the results do not change. Okay, so that's a way to say that we don't have a transient phenomenon happening in these samples while we are acquiring this data. And second, for example, for the X-ray microscopic, we have also we cannot place them in a chamber because of the nature of the experiment, but we always have a flow of nitrogen trying to avoid any presence of moisture, okay, which is what changes more the sample. Again, for compositional measurements, the atmosphere is not very influential. For photoluminescence measurements, yes, but for photoluminescence, as I say, we perform like different cycles, so we measure the sample several times and we see no change, and then we are happy that they are stable, at least for the time in which we are measuring. Okay, that doesn't mean that if you continue, like in 1 month, the sample is not bad, but still it is good. And then we, of course, we take very care of we are very careful about storing the sample well in the glove box between measurements. Okay, so the samples always live in the glove box unless when we measure them under the microscope. Okay, so just one final comment about this. If we measure, for example, lectin perovskites, we cannot do this type of experiments if we don't encapsulate the sample. Okay. An encapsulated sample means that we cannot measure X-ray microscopy.
Okay, thank you very much for the very detailed answer. And my last one is, I mean, a few years ago, the trend was, to mix cations, mix halides. Now, these days, the trend is to have single cation, like for magnesium, as low as possible iodide. I'm speaking about the photovoltaic application of these materials. So have you checked this type of materials with your measurements? And
yes,
did you get any useful information?
Yeah, so that's going to be, let's say, our next chapter of this type of experiments. This is actually what we are doing now. We are doing this type of measurement now in food devices under operation conditions. So we illuminate it with one sun, but we also apply a bias in the device, okay? And we are exploring the effect of halide mixing, so presence of more or less bromine in the halide alloy, and also the effect of the A-side cation. So we are measuring like single cation, double cation, and triple cation samples to analyze the effect of those samples in the film. Of course, my opinion is that the simpler the composition, the better, because that will give you like a less heterogeneity. But the issue is that usually in this it's very difficult to have a very good, let's say, for magnesium lead-3 iodide, a stable sample. Okay, so usually we employ this alloy to stabilize the sample over time. But if we manage to find a way to stabilize pure compositions, I believe those are going to be the ones we will have that will show lower presence of defects, because you reduce that, let's say, degree of heterogeneity.
Thank you very much for the answer. And we have still 2 minutes, so I can go to the last one from Felix Kosashik. Considering the low X-ray dose used in the synchrotron, Was any kind of data denoising treatment necessary for the nano XRD and XRF?
Not really. In this case, that's a good question, Felix. In this case, we don't need the denoising for these particular experiments, okay? So, for example, if we want to measure a lectin perovskite or like a more confined systems that are less stable than this triple cation, which are very robust, probably we will need to do the measurements much faster in the X-ray microscope, and then we will need to use the denoising treatments, which is something that probably you know, Felix, we have been employing also for the electron microscopic images that we collect in material science.
Thank you very much, Felix, for the question, and Miguel for the answer. Okay, so I see. No, it was just a comment. Great, thanks, Miguel. Thanks for this interesting presentation. So we're just on time. So I would like to thank again Miguel for this very inspiring, interesting, and very informative presentation. I hope you all enjoyed the information that we learned from this lecture. So it was a great pleasure, Miguel, to have you here with us. And I think we can stop now the session and stop recording. So we'll see you in, we will have now our break, and then we will come back with the next speaker again from the University of Cambridge. Thank you very much. So welcome to the third talk of the third day, actually, of our intensive course on perovskite materials and their optoelectronic applications. So it is a great pleasure and honor for us to have another speaker from the University of Cambridge, Mr. Krishanu Day. So Krish studied for his bachelor degree at the National Institute of Technology, Sirkar in India, and he achieved very high score and first honor degree. Then he moved to the National University of Singapore, NUS, for a master by research degree at electrical and computer engineering. And currently he is a PhD student. He will be finishing very soon at the University of Cambridge at the Department of Physics, together with Professor Sam Stranks, working on the optoelectronic applications, including photodetectors and transistors and photovoltaics of metal halide perovskite materials. So today, Chris will discuss about his work, and in general, he will give us an introduction about charge transport of metal halide perovskites using field effect transistors. So, Chris, it's a great pleasure for our school to have you here, and please share your screen and start your presentation.
Thank you very much, George, for the very kind introduction. Can you see my screen?
Yes, I can see your screen, but please put, yes, that's perfect.
That's fine.
Okay, great. Okay. Thanks.
And
you have 45 minutes for your presentation, for your lecture, okay. Plus followed by 15 minutes for the Q&A.
Yeah, okay, great.
Thank you.
Hello, everyone. It's a great pleasure for me to talk in front of you today on a very different kind of device than probably what you have heard over the last 2 days. And that is field effect transistor. It's not a very uncommon device for an electrical engineer, let's say, but in the community of metal halide perovskites, it's still an emerging field, and therefore I try to give you a basic introduction of what this device looks like, what it does, how it does it, then give you a slight introduction of how it has evolved over the years, and then I will share some of the results that I have obtained, but that is not going to be the focus of it. I'll just try to keep it as general as possible, knowing people from different stages of their career. So I wanted to keep it more general. So as George said, I'm currently a PhD candidate. I'll be finishing very soon, in next 1 or 2 months. Um, so, um, so this is going to be the contents of today's talk. Start with the fundamentals of field effect transistors, then talk about emergence of perovskite FETs, then what are the challenges in the field and how do we solve them, some of the examples including some of our own work, and then if you study field effect transistors, what are the other related devices you could look at using some of the insights you get from this. Okay, so a field effect transistor is basically the building block of modern electronic circuits. So in all of our electronic gadgets like mobile phone, tablets, computers, all of them have chips in them, and the functionality of the chip is determined by the transistors. So on the right hand side, you can see a basic building block of a digital electronic circuit. It's called an inverter. So an inverter is a combination of two transistors, one p-type and one n-type transistor, and that's going to be the basic building block for providing all the other kinds of logic gates, which is the basic building block again of digital electronics. So we're going to try and understand how this kind of transistor works, and then look at how perovskites can be used in this kind of devices. So on the left hand side, you can see a very simple schematic of a field effect transistor. So this is a 3-terminal device. So you have a gate electrode, source electrode, and a drain electrode. So it is different from a solar cell or an LED where you have 2 terminals, anode and cathode. So what happens here, you apply a voltage at the gate terminal. Let's say if you're applying a positive voltage, you would generate a negative layer of carriers in this channel layer. So channel is the interface between this semiconductor and the dielectric layer. So you generate an oppositely charged carrier channel here, and you can then change the conductivity, i.e. the mobility in the channel, by providing another voltage at the drain terminal. So you're applying 2 voltages at the same time to operate this kind of device. In the below, you could see that it is showing how the transistors have changed over the years. So the transistor was discovered way back in 1950s, and there is already a Nobel Prize given to 3 scientists on that. And you can see all the revolution in the digital electronics and the functionality of our devices and the speed of operation has been achieved by miniaturizing the dimensions of the device. So this is something like Moore's law. So if some of you have heard that Gordon Moore predicted a long time ago that in a particular microchip, the density of transistors over every 2 years would double, and the cost of that would actually halve. And basically, that kind of law was valid for a long time, and therefore you've seen such fast revolution in electronics. Although recently the pace has slowed down a bit because the things are getting closer to the limit. But even then, there are companies like TSMC, Intel, they are providing more and more innovations there. So the current technology node is about 5 nanometer or something in most of the industries of semiconductors, whereas some of the advanced research is now going on below 3 nanometers and all. So basically, a field effect transistor can have all these kind of 4 configurations. So as it started with silicon transistor, this was the classic top gate top contact architecture of a silicon, because you can't really deposit silicon anywhere. So you're starting with a silicon wafer and like a silicon substrate. You make it n-type or p-type dope, that becomes your semiconductor, and then you deposit the dielectric, source and drain electrode, and then gate electrode. So that was the more classic configuration for a silicon transistor, which is there in all of our devices, but or at most of our devices. But these emerging materials like perovskite, organics, amorphous silicon, which are very easy to deposit using thin film approaches, they can have all these 4 kind of approaches. So basically, depending on where your semiconductor layer is as compared to source, drain, and gate, you can call them either top gate bottom contact, top gate top contact, bottom gate bottom contact, and bottom gate top contact. So as most of you are aware about solar cells, so there are some important characteristics that you always think about when you talk about solar cells, like open circuit voltage, short circuit current, fill factor efficiencies, operational and environmental stability, and hysteresis. And there are some equivalent parameters even in field effect transistor, like mobility. That's the most important characteristic of any field effect transistor, because it measures the charge transport. And mobility, as you know, is the characteristic of any semiconductor that signifies its transport properties. But you also have threshold voltage on-off ratio, subthreshold swing, again, the stability concerns remain, especially for perovskites. There are also additional considerations regarding hysteresis. Remember, the field effect transistor are lateral devices, so you're measuring the charge transport in the lateral direction, as compared to in a solar cell where the charge transport is happening in the vertical direction. So that's one thing you should always remember. So in a transistor, like in a solar cell, you have the JV characteristics from where you find all these different parameters, VOC, fill factor, and efficiency. In a transistor also, you have these kind of two classic characteristics. One is called the output characteristics, where you sweep the drain source bias, and then you measure the change in the drain source current. And there's another thing called the transfer characteristics, where you sweep the gate source bias and measure the change in the drain source current. As I mentioned before, there are two voltages you applied, one at the gate, another at the drain terminal, and both of them can modulate this drain current, and accordingly you have these two characteristics. And from these two characteristics, you can find all these different parameters like mobility, threshold voltage, switch on voltage, subthreshold swing, and all of them using these particular equations. So these are like very classic equations you'd find in any semiconductor book. You must have already studied in physics or electronics in your bachelor's. But these are, remember, valid for something like a gradual channel approximation. So what it means is that your channel length has to be large enough so that your gate terminal can control the carriers in the channel. If the channel is too short, then the contact resistance at the source and drain contacts would dominate over the gate, and therefore these equations then would not be valid. So in our case, for perovskites, as you see, these are comparatively long channel devices, so therefore we can for certainly use these equations to find all the necessary parameters. So how the emergence happened for perovskite FETs. So before that, what are the different ways to measure charge transport in perovskite? So this is one of those classic graphs showing different perovskite compositions and different approaches used to measure the mobilities. Some of them like terahertz or time of flight, or even microwave conductivity, which is not shown here. These are optical based approaches, so you don't necessarily need any contacts on them. You could measure them on bare films. And this is one of the ways spectroscopies would like to measure the mobilities. However, you should always remember that these approaches give you an ensemble mobility of carriers, so you can't really distinguish between electrons and holes. But there are also electrical approaches which are based on contacting the device, like space charge limited current, Hall effect, as well as like field effect transistor. So field effect transistor is indeed much less explored. As you can see from the data points here, there are very less data points for that. But why is it important? Because it is a long range transport properties as compared to these electric optical based approaches which measure local transport. This field effect transistors can really give you an indication of long range transport. It is also sensitive to carrier polarity, so you can really distinguish whether it's a hole moving or electron moving. You can also probe ionic migration, which is a big thing in halide perovskites, and therefore all of these properties make them quite relevant for all kinds of devices, to be honest, as you would see in the upcoming slides. So the first demonstration of perovskite FET happened way back in 1999. So basically, about 10 years before the first perovskite solar cell paper came out, there was a paper on perovskite FETs, but it was unnoticed for quite a long time. This paper came out from IBM, from David Midzie's group. So they looked at a 2D tin perovskites like this phenethylammonium tin iodide as the semiconductor layer in these field effect transistors, and they then show quite nice gate modulations, meaning that these materials can indeed be applied in field effect transistors. At that time, they noticed that if you increase the dimension from this is a pure 2D, if you want to go to a pure 3D transistor, that doesn't seem to work. So their gate cannot really control that channel. And that's because at 3D tin-based perovskites behave more like metals. So for transistor to work, you need the semiconductor layer at the channel, not a metal layer, so that you could really deplete any channel. For metals, there are so many carriers that it's not possible to deplete. So that's why the 3D perovskite based on tin was not really explored at the time. But indeed, even in the 2D perovskite, the mobilities were quite moderate, about 0.5 or something. After that, there were more studies that followed where they changed the A-side cation from PEA to fluoro-PEA. The saturation region mobilities were not really improved much, but it was just a demonstration that you could use different kind of A-side and still get them working. Just to remind you, what is the saturation region? So this comes from this output characteristics of any device. So you could see that in the beginning, the drain current follows the drain voltage almost linearly. So you call this a linear region or a triode region. And then you have this region at some point when the drain current becomes almost constant or increases slightly over with respect to the drain bias, and you call them a saturation region. Okay, next, there were more efforts now to deposit similar kind of materials by other approaches like evaporation, and you could already see the evaporation gave them quite good on-off ratios. So on-off ratio is very important properties, again, of any transistor, because you don't want your transistor to be on all the time, so you're going to consume a lot of power, and you don't want to do that. Like in a mobile, you would want them not to lose your battery when you are not using that. So therefore, the on-off ratio of any transistor that's there in the chip needs to have a very high value. Even threshold voltage needs to be lower because you don't want to give them a lot of voltage in the beginning to start working. And again, at the same time, you don't want it to be too low that it's already on. So you need to have some of the compromises that I mentioned. But all of these devices, as you can see, was based on 2D perovskite, because at the time 3D perovskite was not really in the scene. But in 2009, when 3D perovskite really came into the picture and solar cell efficiencies went up very quickly, people tried to look back and try to then use these kind of materials in transistors. So you could see this is a nice demonstration in 2015 where they used this methylammonium lead iodide chloride, which at that point of time was quite a popular composition. If you see the very early papers of perovskites, you see that there's always some amount of chlorine being added in this MAPI materials. So it made the material properties better, device efficiency is much higher, and therefore people tried them even in field effect transistor, and they found that it is indeed possible to work with these materials even at room temperature. So you could see that these materials gave them mobilities about 1 or a little higher than 1, and on-off ratios at the point of time was not that great. Of course, there is chlorine in there, so there was some doubts whether there is some doping from that, but what I'm trying to show here is that how the perovskite solar cell field evolution really drove the evolution even in the field effect transistor field. So you would see even in the upcoming slides, the materials being tried in FETs are all corresponding to those which have been tried in solar cells. Then even in 2D perovskites, the kind of exploration continued, where what happened is that people then tried to modify the interface between this dielectric and the semiconductor using some self-assembled monolayers. So this is basically to pacify the interface, because the subthreshold swing that I mentioned before is dependent on how much traps are there between the semiconductor and the dielectric. So you could passivate some of those with adding these kind of passivation or self-assembled monolayer treatments. At the same time, you have these contacts which will inject the carriers, but depending on the work function of your material, there might be some injection barriers that are there, and you would like to get rid of them, and therefore people use different other hole injectors like moly oxide or something. And you could see they tried very different configuration of transistors. This is bottom gate, bottom contact, bottom gate, top contact, bottom gate, top contact, top gate, using different interface modification, different hole injection layer. You could see all of these modification gave them quite nice improvements in the mobilities. So they could reach even up to 12 centimeters square per volt second, which is indeed a very great number for a material that is processed so cheaply using a solution-based approaches. Remember, silicon with 3,5 materials, which are used a lot in transistors, they are deposited using very expensive and sophisticated vacuum-based approaches. So compare that with perovskite thin films, which are deposited using solution-based approaches. These kind of early developments were quite promising. At the same time, triple cation became a big thing in the perovskite solar cell field. So people tried them even in transistor and found that triple cation very nicely have an ambipolar transport. So basically, how do you understand it's a p-type or an n-type transistor? So if you are sweeping the voltage in the positive direction, and then if you see the increase in the drain current, then you call it okay, I'll explain to you in a better graph. I think this is not very clear, but just to tell you that ambipolar means it can allow the transport of electrons and holes with very similar mobilities, and they found that adding some cesium helps to improve their mobilities, which is also the case even in the triple cation solar cell paper from Michael Saliba, which showed that cesium was used to improve the perovskite efficiencies as well as the stability. So the same thing really followed up here. And why is an ambipolar transport or ambipolar semiconductor important for a field effect transistor? Because you could then use the same material both as an N-type FET and a P-type FET, and then make an inverter out of the same material, basically. So that was quite nice. And for ambipolarity to exist, it is important that there is no background doping in these materials. And in lead perovskite, it is indeed the case where you consider the perovskites or the lead perovskites in particular to be almost like let's say undoped, almost undoped. I wouldn't say completely undoped, but almost undoped. Compare it with silicon, which is, you could see already here, silicon is P++, so it's very, very heavily doped. But in perovskites, lead perovskites in particular, they are not really that highly doped, and therefore you could use the same material both for P-type and N-type transistor. But then all of these things were just like exploring these materials and different device structures to see how much mobilities can be achieved. But then we needed to understand how this 3D perovskite FET functions. So what is the charge transfer mechanism in a field effect transistor using 3D perovskite? So this is a very nice work from Cambridge. That what they looked at is did a bunch of temperature dependent measurements. So they went to lower temperature up to 100 Kelvin, and they did it also near room temperature. And then they found that the mobilities at low temperature are much higher than at room temperature. And for a normal semiconductor scientist, you would think like this is a classic phenomena of a lattice scattering, where at low temperature the lattice doesn't vibrate that fast, or the phonon effect is lower, and therefore you would effectively see an increased mobility. But what they found is that this kind of hysteresis that basically signifies, even in a solar cell, presence of some ionic migration effects. They found that this ionic migration effects is basically the reason why the mobility at low temperature is higher than in room temperature. So you can see them much clear in this particular graph, where they plot this transistor mobility as a function of temperature, and you can see that there are three particular regions of interest. This particular region near room temperature, called region 3, was the most affected region if you change the concentration of perovskite. So you could see if you go down to 0.25 molar, so very, very thin perovskite, and accordingly very low grain sizes, you start to see the reduction much more significantly in this region 3 as compared to in a thicker film of let's say 0.75 molar. And as you would imagine, in a thinner film with smaller grains, you would have a lot of grain boundaries, and the grain boundaries are one of those channels for transporting the carriers, not the carriers, transporting the ions, and therefore you would ideally want to have less grain boundaries to have the less effect of these ionic migration. So basically, it was postulated that near the room temperature, the reduction in mobility with temperature is indeed because of ionic migration. So how does ionic migration basically affect it? I'll tell you a bit later. Like, how does an ionic migration reduce the mobility? So you would, of course, imagine that there is an ionic migration here, so you would start to see some hysteresis. But why should it decrease the mobility? I'll come to that in a short while. But there's also this region 2, which is basically attributed to the presence of methyl ammonium in these compositions. So these are done on methyl ammonium lead iodide field effect transistors. And methyl ammonium, as you would know, have dipoles which can rotate quite freely near room temperature again, and they have something called a dipolar disorder associated with that. And this dipolar disorder basically prohibits to some extent the transport of carriers through the channel, and therefore at lower temperature, when this dipolar disorder effects or the motion of the MA dipoles kind of freezes a bit, you start to see higher and higher mobilities here. So there were two things here. What are the two things? And these are the challenges. Basically, one of the main important challenges is the ionic screening of gate potential. So let me explain what does that mean. So you have a gate electrode here. When you apply a voltage at the gate terminal, ideally what you want is that if you are applying a positive voltage here, you want the electrons to be accumulated at this particular interface, which you can then use it as an n-type field effect transistor. But remember, these are perovskites, so they are electronic ionic semiconductors. So this positive bias can also attract iodides at the interface. So not only the electrons, but also iodides can move here, and they can also accumulate at this interface. And as you can imagine, if there is a layer of iodides here, that will already take a lot of these, that will already be experiencing most of the potential that you are applying at the gate, and therefore the modulation of the gate on the carriers, i.e. the electrons, goes down, and therefore less influence of gate you have, lesser will be the mobility here, and therefore more ionic screening would lead to less mobilities. And therefore near the room temperature, because the ions can move faster, the screening of the gate potential is much higher, and therefore the mobility goes down. And that's the reason why you see in this region mobility goes down as you go to higher and higher temperature, where the iodides can move a lot faster. The other issue, as I mentioned, is with the presence of methyl ammonium in most high performing FETs till, let's say, 1 or 2 years ago. And even in the solar cell field, you would see for the first 10 years methyl ammonium was a big thing. So all the high efficiencies were used, we're having like methyl ammonium as one of the constituents of the A site cations. But remember, this methyl ammonium, as I said, have this dipolar disorder, which is again a problem when you consider them for FET applications at room temperature. And third thing, and this is something going back to what I mentioned in the beginning, in the tin containing perovskites, it was quite impossible at that point to modulate with the gate terminal because of uncontrollable doping in these materials. So basically they behave more like semi-metal as compared to a semiconductor, and therefore you can't really use them in the field effect transistor. So these are the three big issues, and there are like some approaches to solve those, which I'll quickly go over one by one. So this is one of those papers which looked at multi-cation approach. So you could see they started from methyl ammonium iodide, then put a double cation like FAMA, then moved to a triple cation, cesium, and then you can also go up to quadruple cation, rubidium, cesium, formamidinium, methyl ammonium. This is again inspired from the field of perovskites, where they immediately found that the triple cation is good, but you can also have 4 cations. Again, coming back from those early days in EPFL, where all these kind of breakthroughs happened, and so people tried to replicate those even in field effect transistor, and they found that indeed, first of all, the mobility is increased. If you put double cation here, you can already see here that there's more currents, therefore more mobilities. Also, they found that even at the room temperature, there is less hysteresis as you have more and more cations there, as compared to in a methyl ammonium lead iodide, which even at low temperature has got some hysteresis. Using more cations at the A site was a nice way to first improve the mobility, but also reduce these ionic screening effects, as I mentioned before. And how to see if the ions are moving or not. So this is a very nice microscopic way to visualize ion migration. So these are a lateral device. So you have the two contacts, drain and source, but there are a lot of channels close to each other. So you could see this is a cross section of a device. So you measure a PL image of this cross section before applying any voltage, because at the end of the day, for field effect transistor, you need to apply some voltage. So you see, before applying any voltage, the PL looks very uniform all across the channel. But as soon as you apply some voltage there, you see that there is some preferential increment in the PL near the source electrode, right? And there's the reduction near the drain electrode. You don't really see that effect as clearly if you have a longer channel device like 100 micron. And so what you could imagine is that this is happening because of the application of bias. So imagine you have a 20 micron versus a 100 micron device, and you are applying the same voltage. So the electric field is much higher in these shorter channel devices. So what does the electric field do? So electric field would move the ions. So this is a MAPI n-type FET. So you're applying a positive bias, so it will move iodides also. So iodides are there all across, but remember this is source, so this is grounded, so iodide is negative. And so it will try to go to the positive electrode, which is your drain here. So as more and more iodides start to migrate towards the drain terminal, you start to have more and more iodides accumulating, probably as interstitial iodides. And there are some nice papers from our group in Cambridge showing that iodide interstitials are deep traps in perovskites, and therefore they can cause non-radiative recombination of charge carriers, and therefore applying the voltage would reduce the PL in the drain electrode, possibly because of the accumulation of excess iodides. But what they found is that if they go to a quadruple cation or even a MAPI, but with some treatment of methyl acetate or something like that, or some Lewis base, they found that this kind of effect is much more minimized even after application of bias. And as I will show you a bit later, these kind of measurements can really tell you whether ionic migration in a device is decreased or increased, and you can then correlate that with what you see from a temperature dependent transport properties. There is another paper again from Cambridge that tried to look at this so-called cleaning method, so CHC strategy, to reduce the ionic screening. So basically these ions, motion of ions is also related to the presence of defects, many of them at the surface. So what this particular study wanted to look at was how to make the surface much more clean, so with less amount of defects. So they adopted a three-step strategy. First step is called the cleaning step, where you basically apply something like an IPA. So you remove all the dangling bonds and all the functional groups, something which are like attached loosely at the surface. So you remove them with some solvent like IPA. But IPA can also dissolve methylammonium, so you can also remove some methylammonium together with that, which you actually don't want. So in the second step of healing this MAI deficiency, you apply another kind of solution, now having an extra methylammonium. So what you do is that you are healing some of those deficiencies that you create after the first cleaning step, and at the last step you do another second clean, so that after this particular healing step, if there are some more defects at the surface which are left, you can actually clean them with a further cleaning. So this kind of cleaning approach really helped them to achieve much higher mobilities near the room temperature and as low temperature, and they show this kind of behavior is kind of more general across different lead perovskite compositions, including double cation, triple cation, and so this was a very nice approach, showing that if you can passivate the surface, you can also minimize some of those effects of ionic screening. Of course, it will depend on what the structure of the perovskite FET looks like. If you have a bottom gate, bottom contact, where your perovskite surface doesn't have anything to do with your channel, it's the bottom interface which is limiting, then this kind of treatment will not give you any improvement. Whereas if you are using a top gate approach, where you have the channel near the surface of perovskite, then this kind of approaches can really yield much better outcomes. And then we also had our own approach to deal with this kind of ionic screening as well as this MA problem. So what we did was then to look at a mixed lead-tin composition, which is basically the focus point of my PhD. So we looked at the mixed lead-tin composition with a variety of A sites, as I will show you later, and we used a very standard bottom gate, bottom contact architecture, and these are the different materials at the source drain, channel length, and what dielectric we used. And then why are these materials important in the first place, beyond just FETs, is that these perovskite materials can really lower your band gaps. So all the perovskite with lead compositions cannot really give you any band gap below 1.48. So as from the talks you have heard, I think in the last 2 days or even this morning, you would have heard mostly about lead perovskites, but remember, they cannot really give you band gaps anything below 1.48 electron volt. But if you look at a Shockley-Queisel limit of efficiency versus band gap, you would see that the maximum efficiency lies somewhere between 1.3 and 1.4 electron volt, which cannot really be reached with only lead perovskites. And also in a more two-terminal or like a four-terminal tandem, like two-junction or even a multi-junction configurations where you have two different semiconductor layers which will absorb different parts of the solar spectrum, you need a high gap material at the top, which can easily be given by a lead perovskite. But for lower gap, you need something between 1.1 and 1.3 electron volt, which again is not possible with lead perovskite itself. Therefore, the importance of lead tin perovskite lies here, because it can lower the band gap down to about 1.2 electron volts. So they find the application in both these two kind of approaches. So it's also there is also benefit of lead tin perovskite beyond just this FET approach, as I show. So what we started to do was to let's again start with the 3D perovskite. So different compositions of Ma, Fa, and even cesium Fa. And we found that again we couldn't really see any increment in the gate, drain current as you are sweeping the voltage. So the current is flat. So that's what we called no gate modulation. So you can't really modulate anything with the gate terminal, and that's because of semi-metallic behavior. As I said, you could see there's very high current already in the off state. So you don't want to use any this kind of materials for your transistor. Then what we started to then think about is, okay, let's take a more gradual approach. So let's start with the lead perovskite first. So this is the green curve, shows you lead perovskite. So this is a cesium Fa lead perovskite. So we started with an Ma-free composition to start with. So already we can then get rid of one problem, which is your dipolar disorder. But then we wanted to see if the ionic screening effects are also kind of minimized in that way. So you can see for the lead perovskite, you start to see an increase in the drain current when you are applying the voltage in the positive direction. So when you're applying in the positive direction, you're seeing an increase in the drain current, and that's what we call an N-type transport, because this positive gate bias will accumulate a carrier of electrons in the channel, and therefore this channel then can be modulated with a further application of the bias in the drain terminal. You can see here, and therefore the current increases there. But what we found quite interesting was that as soon as you introduce some amount of tin, so let's say from 25%, we start to see this trend completely reverses. So now the drain current increases, but when you are sweeping in the negative direction. So that means you are changing the nature of transport. So this is N-type transport. Now you're having a P-type transport here. And from these two characteristics, transfer characteristics, you can find the mobilities, and we find the mobility increases consistently with amount of tin in the composition. And basically what you find is that we can reach a maximum mobility of 5.4 centimeters square per volt second for this optimum composition of 50% tin, which at that point of time was one of the highest mobilities obtained in 3D perovskites, not only lead tin, but even in the lead perovskites. Then you can also see that in the output characteristics of such a lead tin device, there is very little hysteresis, as you could see. Even you could see from the comparison between the transfer characteristics, where the lead perovskite has quite a lot of hysteresis, whereas the lead tin has little hysteresis. So I wanted to see if this means that in the lead tin perovskites there is less ionic screening effect. So we did some scan rate dependent measurements. So it's very classic measurements even done in solar cells, where you vary the scan rate and then try to see if the hysteresis properties change or not. And what you see here is that for the lead perovskite, as you are changing the scan rate here, the hysteresis also changes. So that means the ionic motion is very relevant here. Whereas for the lead tin perovskites, we see that even if you change the scan rate, there is very little change in the hysteresis. So this was kind of a nice first demonstration that ionic screening effects possibly is lower here. Important to note that we didn't go anything beyond 50% tin, because you can already see for 75% tin there is very little change in your drain current. So again, this is becoming more like this pure tin perovskite, which is uncontrollably doped. Then we also looked at a variety of A sites. So you could see here, this is a cesium Fa variation. You can see that some amount of cesium is good. You could see 15% cesium was kind of our optimum. That's what we used in our previous experiments as well, what I showed to you. we deliberately also introduced some methyl ammonium in a separate experiment to see what happens if you have methyl ammonium in a lead-tin composition. Again, what we found is that compared to a pure Fa, the dual cation, both with cesium and in methyl ammonium, gives you a better mobility. This is also seen from the early papers of perovskite solar cells, where there's always at least a double cation, if not triple cation, in your A site. You can see the dual cation always gives you better numbers. For methyl ammonium, we didn't really go beyond 40%. Because you could still already see that at 40% there's already a lot of hysteresis it's beginning to appear. We didn't want to exacerbate the hysteresis by going to further higher MA content. So what we then basically wanted to do was to basically look at this kind of transport measurements as a function of temperature, because this can tell you about the mechanism of transport, which is what we are interested to do here. So you can see that for a field effect transistor, mobility versus temperature, you see the classic behavior which I showed to you before. Remember, there is no region 2 here because there is no MA cation here. So you already see one region, which is the reduction of mobility near room temperature, which you can easily say it's due to ionic screening effects. So this is very usual, but as soon as you introduce some tin in there, you start to see that this trend again completely reverses. So there is now no negative temperature coefficient being observed near room temperature, so it's now all positive. So it shows a temperature activated behavior, which suggests more like an hopping transport in these devices. We could also fit this region using an Arrhenius plot, and you can find the activation energy. So what the activation energy in this kind of measurements tells you is how deep your electronic defect is below your transport level, and your transport level is very close to your either the valence band edge for hole transport and or the conduction band edge for your electron transport. So basically we see that for the optimum composition of 50-50 lead tin, we see that the activation energy is much lower, which means that the defects in these materials, electronic defects, not ionic defects, are quite shallow. And people who are aware about this field of tin perovskites would know that there is a lot of tin vacancies in these tin based perovskites, which are known to be shallow from theoretical calculations. So this could be one of the reasons why we see much shallower activation energies in these materials. We wanted to see also there is a different trend that happens below, let's say in this region 160 or 170, 180. So whether this kind of transition is related to any structural phase transition in perovskites. So we did some temperature dependent X-ray diffraction measurements. So these are done on thin films with multiple A site, as you can see, multiple B sites. So this very complex composition. Therefore, we can't really resolve a very sharp transition. But what we can definitely see in this particular plot, you could see that over this temperature range of 122 Kelvin to 182 Kelvin, there is a phase transition region present, which is smeared over a larger temperature range due to the polycrystalline nature of the films. And this is already nice too, because you can see in this particular range, we also have this change that you can see here in the transport. So there is possibly some relation between the structural phase transition and this transport behavior, but further detailed study needs to be done to conclusively establish those correlations. But then we also further wanted to look at what happens if you have a methyl ammonium there. And you can see even in a lead-tin perovskite, which normally shows a positive temperature coefficient, if you introduce some methyl ammonium, you start to see again one of those this negative temperature coefficient that kind of arrives even in this kind of plots. And the temperature where this transition from positive to negative happens goes to lower temperature as you introduce more and more methyl ammonium. So this is 15% methyl ammonium, this is 40% methyl ammonium, and we see that this temperature, transition temperature, goes down. So that really tells us that this is related to the presence of methyl ammonium that starts to reduce the mobilities, possibly because again of the dipolar disorder induced ionic defects. So this is again another quite nice indication telling you that even in a lead-tin perovskite, which seems to be having less ionic screening effects, you still don't want to use any methyl ammonium because it can reduce your mobilities near room temperature. We wanted to again visualize whether the ionic transport or the ionic screening effects are much lower in these lead-tin perovskites. So what we did was take again this kind of measurements. So this is a pure lead perovskite. So this is before any biasing. So you can see the channel PL, and then you can apply further and further biasing, and you start to see that, oh, there is reduction in the PL in the channel, and this kind of this reduction starts with the drain electrode and kind of percolates through the entire channel. So this is very classic signature of motion of iodides. But if you compare this with the pure tin perovskite or mixed lead tin perovskite, you find that after the first biasing cycle, there seems to be some change, but after that, there is very little change. So this is a very significant reduction of such behavior as compared to lead perovskites, and this particularly tells you that the ionic screening effects are much more minimized in these kind of devices. And this is basically the mechanism that we suggest. So particularly in this lead-tin perovskite, these are p-type transport that I showed to you before. So we are not necessarily having iodides at the interface in the first place, but you can still have this A side and B side in the interface, which can possibly also have the ionic screening effects because they are charged. But even if they are present, we think that they have a chance of forming some neutral defects with this negatively charged tin vacancies, which I mentioned before, and which are also the reason for this uncontrolled hole doping in these materials. So as soon as you produce some neutral defects, you don't have any more ionic screening, because for screening to happen, you need to have a charged defect. And we also see that in the lateral dimension, we see that in the in-plane direction, the ionic screening or the ionic migration effects are much suppressed in the tin-based perovskite as compared to the lead-based perovskites, and we also have no methyl ammonium here. So there is no such factors that I mentioned before was a challenge in the field. We tried to solve all of them in this particular study, there is therefore there is more studies now looking at tin-based perovskites. So this is one of those studies looking at almost 3D, but there is some 2D templating layer for the transistor to work. The mobilities are not very high, but it shows that you can really use tin in these devices. This is another nice study where they use an inorganic cesium tin iodide perovskite as a transistor material, and they found very, very high mobilities, close to or even more than 30 centimeters squared per voltsecond, which is really great, showing that these can really go up to very high numbers, provided more and more people join this field. And then in the last two slides, what I'll show you that what are the other benefits that you can have by studying field effect transistors with perovskites. There's also a related device called a perovskite light-emitting transistor. So you have heard about light-emitting diodes. You have now heard about transistor. So you can mix both of them and you can get a light-emitting transistor. So what you can basically have is that in a transistor device, you inject hole in one direction and electron in another direction, and they would meet in the channel, and therefore when electrons and holes would meet, they would radiatively emit some photons, and therefore this is another way of seeing a light emission from a device, but now in a lateral device. And this is quite nice because you can see where they're actually emitting from, because you can really probe them microscopically very easily, because in the normal vertical LEDs you have a lot of layers at the top, so it's hard to probe where the emission is actually coming from. But in a device like this, you can really probe them with a microscopy, and you can also control this with a gate, because at the end of the day, motion of the carriers here is determined finally by the gate terminal. So the light-emitting transistor is another very cool concept. Important thing to remember here is that this would only happen in a perovskite which has ambipolar transport. So if you have a material which preferentially likes to have holes move much faster than electrons, then you can have these emissions, but maybe more near one of those diodes. But if it has to happen bang in the middle, you need to have ambipolar behavior. And also there's another thing called perovskite phototransistor. So you know about photodiodes, but what the photodiode does is that it detects how much photons it's receiving in the form of electrical current. And a transistor also outputs you some electrical current, although in a dark normally, but if you also use a light, so it can also detect that light, and compared to normal photodiodes, vertical photodiode, these kind of perovskite phototransistors are much better in terms of amplifying the signal, so you have a lot of gain much higher than normal photodiode, and you can also switch it on and off very quickly because you have another lever called gate, which you do not have in a normal photodiode, so you can really turn off whenever you want, so switching speed is also much better. With this, I am almost close to my presentation today. So thank you very much for listening to my talk, and in the next few minutes, I'll be very happy to answer any of your questions. Thank you so much.
Thank you very much, Chris, for this very interesting, detailed, and informative presentation for our intensive course. So now we have 13 minutes left, so I can start the Q&A session. And the first question is from the chat from Apostolos Panayotopoulos. Thank you for the interesting talk. I have 3 questions. The first one is related to the operation lifetime of that kind of field effect transistor, in parentheses, months, hours, compared to other metal oxide semiconductor counterparts. So let's go one by one.
Okay, yeah. Thanks, that's a great question. What I didn't show here was how you actually measure the stability of these devices. Of course, in a solar cell, you could measure them in various ways. You could really put them under one sun for a long amount of time, or you could do a damp heat stability where you have high amount of relative humidity, high temperature, and one sun. There is till now what is lacking in the field of perovskite transistor is a consensus on how to basically best report the mobility, best report the stabilities. But inspiring from other fields, there are some approaches which people adopt, including in our paper, which should come out soon. You'd see that there is something like current stress and voltage stress bias stabilities, where you apply the drain and source bias for a long time, and you measure this transfer characteristics every few hours, and therefore you could track how the mobility and threshold voltage and all of those change as a function of time. So that's one of the ways to measure the stabilities. In terms of how long it is currently, I think because of these ionic migration effects, they are not really great. Again, we still don't have any metric to say what is the lifetime, because in a solar cell you have like T80, T50, whatever. In transistor we don't really have any of those things. But I would say it's still in few hours. If you want to still reliably have high mobilities, it's still few hours, because the ionic screening is a huge problem. Remember, in a solar cell, you have only 2 terminals, so you are applying only 1 bias. Here you have 3 terminals, so you're applying 2 bias. So the ionic screening is much more significant here. And so I think if we can really get rid of those ionic screening effects, this kind of stabilities can be far improved.
Thank you very much for the answer. Let's go to the second question of Apostolos. The second one is linked to the degradation of the electrodes used in FETs and the effect of the device's interfaces.
Yes, that's another thing which is important. There are many reports. You can see if you type perovskite FETs, electrochemical reactions happening at the interface, that indeed can happen. As you can imagine, the iodides can move, even methylammonium can move, and they can reach one of those source or drain electrodes and do some funky stuff at the interface, and therefore it can really degrade that interface. And field effect transistor is an interfacial device, so you don't want the interface to be degraded. So in a way, it's again relates back to this ionic screening effect. So if you can kind of freeze the motion of ions to some extent, you wouldn't have those kind of electrode degradation occurring due to these ions, and therefore you could prolong the operation of these devices.
Thank you very much for the answer. Let's go to the last question of Apostolos. What type of self-assembled monolayers are being implemented in field effect transistors? I believe the perovskite ones, and explain a bit more about the effect on the surface observed after the deposition. Thanks.
Right. So there isn't a lot of different self-assembled monolayers that have been tried in the field. Some ammonium, I don't really remember what the name of that particular SAM is, but you could, if I go back to that slide, is quite so yeah, so you could see this is some SAM based on this ammonium iodide based moieties. What it actually does is also not really known, but in terms of effects, what it does is that, so if you consider about a perovskite transistor where you have a, let's say, silicon oxide dielectric and you are depositing perovskite after that, so that particular interface where the silicon dioxide meets your perovskite, that's where the channel is. But how a perovskite forms on top of silicon oxide, that's another question. You know, like even in a solar cell, depending on what hole transfer materials or what electron transfer materials we are depositing before perovskite, it would modify the properties as well as the morphologies of perovskite and also modulate the defects of the perovskite. So you're doing, if you do something in the surface of that silicon oxide, in this case, you possibly make the surface less effective in terms of forming defects after the deposition of perovskites. But what kind of defects those are and how they passivate, it's still unclear. So that needs to be done more comprehensively in future.
Thank you very much for the answer, and Apostolos for all three questions. So let's move to the next one from Timothy. Hi, very very nice work done on field effect transistors. Do you foresee any challenge in using high K dielectrics to reduce the gate voltage operation?
Yeah, that's a very good point. As you'd already see, we are in this particular case, and even in the broader community, till now, silicon oxide is the most common one, because people have silicon wafers and you can thermally grow silicon oxide on top. For high K dielectric like zirconium oxide, hafnium oxide, there is some studies recently being started to be done. Again, we need to do that, because the point is right that if you look at these materials, we are using voltages up to 60 volts, which is really not great. One of the ready ways to reduce that drastically is to use a high K dielectric. But again, depositing a very conformal and good layer of high K dielectric is not a very trivial task, and also we don't really know how the perovskite would form on top of those kind of high K dielectric. So those kind of optimization needs to be done, and I would say recently there are more people who are trying high K dielectric to reduce the operation voltage to few volts, let's say, because we ideally want to go back to millivolts if possible, because 60s of volts are very, very high. You don't want that.
Thank you very much for the question and Chris for the answer. We have a comment from Easter. He's looking for an advisor for starting graduate studies. We will keep it in our mind, and then we will let you know if there is any opening soon. So I don't see any other questions or comments, but I have some, Chris, if may I. So, like, it's a very interesting topic, actually, to see that this type of materials are used for a variety of applications, including the field effect transistors. So how do you see, I mean, the potential of this type of materials for this application, about, in your opinion?
What I think, to be blunt, I don't see a hybrid perovskite ever being used for a commercial field effect transistor. I think that's not possible, because you can minimize the ionic screening, yes, but you can't really get rid of them completely. All inorganic perovskites may have some, let's say, chance, but again, not with lead perovskites for sure. It has to be with tin perovskite, because mobilities of lead perovskites for any compositions are much lower than tin perovskites. It comes from its electronic structure. It is not going to be very highly mobile semiconductor. But with the tin perovskites, as you can imagine, the stability is a big concern. The tin 2 wants to oxidize to tin 4 very readily. So there is this challenge. If this tin oxidation problem was not there, I would have said the tin perovskites definitely have a chance for commercial applications. But I think right now it's a distant thing. But I don't think hybrid perovskites ever has any chance. I think what we have also tried to show here is that in our paper at least is that we are not really trying to show a new material which can be used in electronic applications. We are using the field effect transistor as a platform to study this ionic migration and understanding the mobility. So it's not about devices for the sake of it. It's more about understanding the science of these materials, which I think is quite pretty cool.
Yes, indeed. Thanks for the answer. I have another one that is related to your composition. I have seen you have only used pure iodide perovskites for your measurements and for your materials and devices. So, are you considering putting some bromide or chloride or any other halides in the composition in the future, and why you have focused only on the iodides?
Yeah, that's a good point. So basically, we wanted to first of all start with as less uncertainties as possible. So because this particular project was basically to try and see if ion screening can be minimized a bit. So we wanted to keep the composition as simple as possible, so not really mix too much with iodides and bromides. But after that, we have definitely tried iodides and bromides, different bromide ratios we have tried. Problem is with the lead tin compositions and bromides, the film quality is not great at the moment. You can imagine this kind of measurements. So this is dependent on long range transport. So your morphology as well as the defect properties need to be very, very good to get high mobility. So we have the data. Mobilities are quite low. On-off ratios are also not very great. And you can see even in a lead tin solar cell field, people really stick to iodides mostly because of the band gap reason for them. But I think we have some data which are trying to see what happens with that. But currently the results are not great with bromides or even iodide bromides.
So thanks a lot for the answer. I have one more that is related to the surface passivation. This is an approach that has been used very efficiently for different photovoltaic devices, for perovskites, or for probably for LEDs as well. So what do you think about using surface or bulk passivation for in this type of materials for the FETs?
Yes, absolutely. I think this is a very important area that people should look at. I would have loved to look at all of those things, but there's time limitation. But yes, indeed. I mean, till now, the focus of the entire community is to see what materials work in FETs, to be honest. Because in the first 10 years, 3D perovskites were not really working at room temperature. It's only in the last 5 years that people have tried to make them work at room temperature. So the idea till that time, like from 2015 onwards, has been to just try new materials. But I think once every material has been tried, now there will be more focus on how to make them even better. And bulk passivation as well as surface or even in the below interface passivation is certainly going to help, I think. As in solar cells, I expect the mobilities to go much higher, and you also can really have a reduced ionic migration with such passivation, because even in a solar cell, there are additives which people have used which show them higher performance and also higher stability. So that also may be another lever that people would explore in future to see how we can improve the FET mobilities further and, if possible, reduce these ionic screening effects.
Okay, thanks a lot for the answer. And my last one is, for example, we see in the beginning of this field, people started using 2D perovskites, and I would say that, to my opinion, this might be the most promising pathway for using perovskites for perovskite FETs. So, I mean, have you seen any work on this new phases of the 2D perovskites being applied, or what is your opinion on applying this hybrid 2D perovskites on the FET?
That's good. So 2D perovskite is the 2D perovskite with the phenylethyl ammonium is the most widely studied FET material in the field. I have shown you maybe on 2 or 3 examples, but there are 20 or 25 in the field. What those different studies did is they kept the same material as PEA2SNI4, which is like the classic material, not with lead though, because with the lead 2D perovskite the mobility is too less because it's very more like insulator, let's say. But PEA2 definitely has good mobilities. I have seen approaches which have taken the mobilities up to, oh yeah, you could see this is itself. This is going up to 12, right? So this is PEA2SNI4 itself. But what the field currently doesn't have is to look at different other 2Ds like reduced copper for like butyl ammonium or something else is not been studied. Dion Jacobson still remains a very open area of research for FETs, and I think Dion Jacobson might have a better chance at these FETs because in the reduced copper you have these 2 organic cations attaching to the lead halide cage on the 2 sides because they are single charged, whereas in a Dion Jacobson you have 1 particular organic cation which is doubly charged. So in that sense, the distance between the 2 lead halide cages is much lower, and you don't want the cage distance to be much higher because then the charge transfer would be prohibited. So I think definitely going forward, DJ perovskites should have to be explored, and who knows, there may be more improvement with DJ18 perovskites in future.
Okay, I think I asked too many, but I think the point here is to get as much information as possible and learn from this type of lectures. So I would like to thank again, Chris. Thank you so much for this very interesting presentation. We learned a lot, and especially on the alternative applications other than the classical ones for these fantastic materials. And also we learned a lot about tin perovskites because we didn't have the chance up to now to discuss and I mean see the properties of this type of materials, and this very nice example of FETs was really interesting for the purpose of this school. So we can stop now this session and we can come back. Actually, we'll stop the recording now. Okay, so welcome everyone to the, while I need people to join, welcome everyone to the afternoon session of our 3rd day for our intensive course on perovskite materials and their optoelectronic applications. So it is a great pleasure to have in this session today with us Dr. Golam Haider. So I will give a short introduction about him and then he will give us his talk, his lecture. So Golam studied physics in the University of Calcutta in India, and also bachelor's and master of science. And then he received his PhD degree from the National Tsinghua University of Taiwan, working on the graphene-based optoelectronic devices. He received his PhD in 2017. Then he stayed at the same university and started a postdoc position in the same group, studying again graphene-based optoelectronic devices. And then since 2018, he is working in the nanocarbon group at the Perovskite Institute of Physical Chemistry in Czech Republic as a postdoctoral fellow. And his main topic of research is spectroscopy of 2-dimensional heterostructures. So the topic of Dr. Golam's lecture is metal halide perovskites for ultra-low threshold lasers. So Haider, please share your screen and start your presentation.
Yeah, thank you very much for the nice introduction. Yeah, let me share my screen and then I will start. Yep. Okay. So yeah, it is indeed like a pleasure to be here and then just share one of just a moment. So I I have shared the wrong screen probably. So yeah.
Yes.
Yeah. So let me reshare it again. And okay, I'll share screen too, and then you will see nothing, and then afterward you will see something. Yep. I hope this is
Perfect.
fine.
Yes.
Yeah.
Great.
Okay. Okay. So yeah. Yeah. So nice to see you again. And then, yeah, obviously it is like a great pleasure to like, speak about this Perovskite lasers. I have some experience like, doing this work, and yeah, it is like Perovskite is really a fascinating platform to do this kind of work. So yeah, let me just share some of the thoughts I have on Perovskite lasers, and then obviously we will discuss in Q&A. Before going to talk my discussion, let me just tell you from where I am. So as just George told, that I am based in Prague nowadays. So this is the institute where I am working on. So let me share the laser pointer of, yeah. So this is the institute where I am working most of the time. And also, so this is the Hiroshima Institute of Physical Chemistry, and this is the Charles University Mathematical Physics Department, where I also work. So this is where I mostly work with low-dimensional systems and with ultra low temperature. And here I am working mostly on, let's say, this optoelectronic devices, obviously perovskite-based devices as well. So yeah, mostly I'm working in both of the institutes together. So let me just quickly move into this topic. So now today's topic is laser, obviously, and I'm sure all of us know about laser now, but let me just quickly introduce what the laser is, and then from there I will actually drive the base of my discussion today, and then we'll move forward to the talks. Yeah. So as we know that laser is an acronym, and it is actually light amplification by the stimulated emission of radiation. Now it has like several terms for light. So the light should be there, and then it should be somehow amplified, and then this amplification should cause some stimulated emission of the radiation, which is light again. So a typical laser device looks like this. So this is obviously a typical laser device, and then the laser device can take many different kind of shape. This is just one example. So here you can see that there are two wall kind of things. Those are two like highly reflective mirrors, and then in that mirror actually confines some sort of optically active medium. So for example, here in this case there are some gas inside, and then there is a source of energy which is exciting this one. And due to this excitation, it will actually start to radiate, and this radiation will actually move somehow like in the fast space. The radiation can go from any direction, but the mirrors are here to give the directionality together with this reflection, which will actually so when there is reflection towards this gain medium, which will re-excite the system again, and that will re-emit, and this process will continue, and ultimately there will be enough sort of lights inside. And if this mirror is a partially reflective and partially transparent mirror, then at a certain time it will start to allow light go out, and on the time we call the system is lasing. Now this is a concept which is valid for most of the laser we are seeing nowadays. And like for example, let's say we have laser pointer, and in laser pointer we just press the switch and immediately the light is shining. So this process caused really very short time for the case of solid state laser. But for the case of gas laser, for example argon laser, helium-neon laser, it may take some time, but this time scale is already very fast, but it takes some times. And even though like it takes also some time to stabilize the system. So those sort of things are like, too much of technical, but today we will focus more of science in it. So let me just remind ourselves again how we create a laser. First, we need a pump source. Pump source means a source which can excite this one, the optically active medium. And then obviously we need the optically active medium, which in laser term, we also call this as a gain medium, where initially there will be a spontaneous emission, which means the emission is uncontrolled. Like, it can be excited at certain time and emitted at certain time. There is no control of it. But this stimulated emission should be converted to this spontaneous emission should be converted to stimulated emission due to some additional effect, and those effect we will talk about. So to create this effect, we need to have an light amplifying medium, which are the mirrors here. But I am mentioning it here again because we will talk extensively about how this light amplifying medium can be changed and how the laser design can be simplified a lot. Now then, again, with the light amplifying medium, we will see how it actually causes to the stimulated emission of radiation. So let me just show you how this stimulated emission causes again in a broader view. So let's say that this is again the same cavity where we have these gas atoms and there are two reflectors. So we initially give by some excitation, we produce a photon source, and this photon travels throughout this medium, and let's say it hit back to this reflector and goes back to the medium again. And when it is traveling too much in this medium, it has a chance to re-excite the sample, re-excite the system, and then the re-excitation will immediately cause also the re-emission. And this re-emission will add up to the number of let's say light photon inside. So these two photons will now then they will travel, and they will again eventually re-excite the system again. And like after coming back to the, let's say from the other reflector, it will re-excite, and then that will add up to the photon again. And this process will continue back and forth, and eventually the system will overcome the loss. And this is a very important thing. I will tell this one again one more time. When the system will overcome the loss, then the light will start to amplify in the system, and that amplification will cause the laser. But laser is not simply light amplification. There should be some other things also. And to understand this, let me take the help of some energy band diagram. So for simplicity, let us consider we have a 3-level system. By 3-level, I mean that let's say there is a ground state, and this is a first excited state, and there is a second excited state. And I will also assume that this first excited state has little bit longer lifetime than the second excited state. And let's say when we are pumping, we are actually creating the okay. Before going to this one, if we have this 3-level system, the Gaussian distribution, the Maxwell-Boltzmann distribution says that the highest number of let's say electrons, for example, highest number of electrons should occupy the lowest energy level. And there will be a distribution of energy electrons over the energy level, meaning that the higher energy level will have lesser number of electron occupation. And this is just this Maxwell-Boltzmann distribution, right? So in normal scenario, we'll have the most of the carriers. Let's say this is again electrons here, and then lesser number of electrons here, and there is even lesser electrons. Now, if we by some means, if we pump those electrons here, and as I said, this is a bit less stable state, so immediately it will by some means the electrons from there will release to this state. And as I was assuming that this is a metastable state, so then the electron will for some time the electron will pause there. And if we keep pumping the electrons from here to here, they will immediately recombine. They will immediately jump here. So this will create more population in the E2 state than E1 state. And this is a situation called population inversion. And now, because this is a metastable system and this is highly populated, if there is an additional, if there is an additional kick from here to just release the system, all of them will eventually release the DXI together, and you will see the amplified light, amplified light. And this situation is like one of the most challenging part for laser, which actually delayed the invention of laser for a really long time. Now, this is a situation where we should actually expect the laser action. Now, for a gas system, or for like like nowadays the laser has been discovered in a wide range of material, and then you will see that this situation is so easy to achieve than what we actually think of. So let me just give you like I will show you those examples later on when you will go through the slides. So now before going to that one as well, like I would like to show, like there should be many kind of light amplifying medium. Previously I was just showing you a plain mirror standing in front of each other, and then the light is bouncing back and forth in between. But there are multiple other choice of optical cavity. For example, you can produce a ring like resonator. There can be like, and in this ring like resonators, the main point here is the main point of light amplification is the interference of light, and this interference should be a constructive interference. And it doesn't matter how you are producing this. If there is a constructive interference, and if there is a loop formation of light reflection, that will lead to laser emission. That will lead to, let's say, this amplified emission. We'll come to the laser part later, because this light amplification and the laser has a tiny difference, which I just told you. Like there should be some other properties of the spectrum as well. The thing is, this kind of ring cavity, or even this kind of cavity where the light can actually create constructive interference, can eventually have the potential to give lasing emission. So it can be a ring resonator, it can be like this, it can be some scattered nanoparticles, or some periodic nanoparticles which reflects the light. It can be some sort of rectangular shape, some weird shape, whatever you can imagine. So the key issue is there should be light scattering, and this scattering should add up to the light gain, so which should overcome the reflection related loss. Every reflection should be associated with some energy loss, and in this closed loop formation, the reflection loss should be overcome by the gain. And this is the key thing for a system to achieve the laser emission. Now, why perovskite for laser emission? Like perovskite has multiple advantages over conventional semiconductors. Let me just go through one by one. Perovskite, like the first thing is, perovskite has very large absorption coefficient from visible to infrared. Now, this high absorption coefficient, many different, like many materials shows high absorption coefficient, and like there are multiple semiconductors which have this property. But the novelty for perovskite is, like you can have, let's say, from visible to IR, and this is a range which no semiconductor can provide. Like you can actually by changing the composition, you can tune the band gap, keeping this high absorption rate, which is unique for perovskite. Then there is like the defect tolerance. Defect is a very crucial parameter for any this light amplifying system, because when there is a defect which actually cause some auger recombination, And this Auger recombination is a non-radiative process. So, and non-radiative process means it is that the emission is not contributing to the radiation. So the system is losing some energy there. And this is very dangerous for any system, to any lasing system. But in case of perovskite, this is actually quite in case of perovskite, this non-radiative recombination is suppressed because of the ionicity of perovskite, and which actually lead to the defect passivation. And then there are other advantages of perovskite, which actually which, let's say, the perovskite has very high quantum yield, which is unparalleled to any other semiconductors, any other conventional semiconductor. Let's say, for example, let's say this gallium arsenide and indium gallium arsenide, they have quite less quantum yield in compared to perovskite. Then there is another factor which is also good for perovskite to overcome the loss, as I was just mentioning about this Auger recombination. Every recombination has their own lifetime. And in case of perovskite, the stimulated emission lifetime is much faster than the recombination due to these defect states. So which is actually good, because before it goes to the defect level, it actually goes to the radiative recombination, which actually suppress the loss due to defect levels. Now, then there is a large binding energy for the excitants in perovskite, which also good thing for lasing system, because when there is a large binding energy, which means you cannot really separate the electrons and holes so easily. And separating electron holes means you are suppressing the emission, right? So when you cannot really separate them so easily, then you actually adapt to the you actually make the system more easy to obtain the light gain than the light loss. Then finally, it is very easy to produce perovskite perovskite semiconductors, unlike other semiconductors which needs rigorous which needs rigorous processing of designing the devices, and all those things are super expensive, and also it needs sophisticated instrumentation to achieve the laser system. But on the other hand, perovskites are, let's say, solution processable, so you can just easily do this in your lab with two different chemicals. You just mix them together, you coat it, and you heat it, and you get the crystal, and which is already good for lasing. So here are some of the crystals I came up with. So for example, here we can just see a very nice hexagonal crystal of this is methyl ammonium lead iodide perovskite, and this is a hybrid perovskite, and this is another methyl ammonium lead bromide perovskite, which you can see the crystallinity is so nice, and you don't need to do very sophisticated lithography on or something else to have this system ready. This is like a major advantage in compare with other semiconducting materials to have the lasing system. Let me just give you some of the example of achieved laser in perovskite. And one of the famous example is like this one here. Here there is a perovskite nanorod, and if you excite the perovskite nanorod with some sort of light source, which obviously excite the band gap emission, and then if you see the excitation emission profile with the excitation power, you can see that after certain excitation power, the emission is getting really stronger. And if you consider this is normal photoluminescence, you see that the photoluminescence intensity is actually remaining pretty much constant throughout the excitation pump, excitation pumping energy density. But at a certain region, you see that the light is amplified a lot. And if you see this in a normal spectrum, it looks like this. Here you can see that when you are actually increasing the pumping intensity. So this previous photoluminescence like spectrum was here, but when the pumping energy is like this is from 550, for example, from this region. So you can see that already photoluminescence is suppressed in compare with the lasing spectrum. Now I call this lasing spectrum because of several factors, and those are like key thing to differentiate on emission from lasing emission to normal photoluminescence emission. And those key things are, let's say, if you plot the emission intensity against the illumination power, then you will see that it will show a pronounced threshold behavior, a pronounced kink in the emission. So initially, when you are like increasing the pumping intensity, your photoluminescence intensity is also increasing. But after certain time, it start to boom, it changes a slope a lot, and you will start to see like much stronger emission than before. So this is one key factor which a laser must have. Then the second thing is, and this is very obvious, so which is like if you see the line width. So the line width, like initially when there is a photoluminescence, the line is really broad. So here it is like 40 nanometer. Now at the threshold power, the line width will abruptly decrease, and it will go less than like or of the order of 1 nanometer. So here in this case, it is quite less than 1 nanometer, and this is the second most important parameter to demonstrate some system is lasing. Then obviously there are a bunch of other parameters as well, who, like for example, if you start to see the if you probe the lifetime of the system, when when the system is like before lasing, so for this is spontaneous emission. The spontaneous emission has their own lifetime. Like you excite the excitation, and then after a certain time it de-excites back, and that has a lifetime. So in this system, for example, the spontaneous lifetime is, let's say here it is like very long, and this is where I was saying that it should say give some sort of metastable state in compare with the other excitation state. So here you can see this is already quite long compared to let's say normal emission. Now if you like when you go to when you start to increase the pumping intensity, there are three different distinguished region, and in this spectrum it is not very clear. So the first region should be that when you are adding up to the like more intensity for the pumping, like this is excitation intensity, the emission intensity should start to increase. And at the first point, there will be a kink showing that you overcome the loss. And this is called amplified spontaneous emission. And here in this case, it is not very clear, but I will give you that example. And this spectra shows actually this amplified spontaneous emission region. And now if you still keep increasing the pumping intensity, you eventually create this population inversion, and you have this lasing action. And this on that time the emission should be stimulated. And stimulated emission means and the lifetime of the excitation is now stimulated by other radiation. So the original lifetime should dramatically decrease. And this is exactly what is happening. So initially the lifetime is much slower. This is a normal emission, spontaneous one. And then this is a spontaneous amplified emission. And then finally, this is the stimulated emission. Now, obviously, this was the threshold behavior I was showing. And here, this is like the emission intensity is much higher, and then the lifetime is also very less. And this is what you can naturally understood, like number of emission intensity is, this means like number of photons, and the number of photons will be more if there is a recombination is more. So and the radioactive the lifetime is actually inversely proportional to the radiative recombination rate. The lifetime is faster means the rate is higher. So here the lifetime is faster means the radiative recombination rate is higher, and when the radiative recombination rate is higher, this means you are having more photons than before, and this is exactly what we can see now. As you can see, the crystals here are so nice, and this actually gives a less defective sample, which makes the lasing threshold so low. You can see this is like, let's say 600 nanojoule, and in normal cases, like the most of the lasers I have been through, it is very hard to get the lasing threshold below 1 microjoule, and it generally goes to hundreds of microjoule, even thousands of microjoule. But here in this case, they got it in nanojoule, which is like really unique. And this is because the structure here, the boundaries of the perovskite, the walls, if you can see here, this you see the dimension of this wall is actually 500 nanometer, which is close to the λ/2 of the emission wavelength. So as I said, close to, if it is of the order of emission wavelength, this means actually the system can behave itself as a lasing cavity. So I was discussing, I was saying that you need to have a emission, light emission medium, and then you need to have a mirror to amplify the emission. But here the perovskite do this job by itself. How it is done? So here the perovskite material works as light gain medium, which is giving the light, and then the boundaries are actually working as the reflector. So you don't need to have an additional reflector to actually reflect to amplify the light in this case. Which is again better than other sources, because then the reflection loss due to other material is suppressed, which is again adding up to the lasing threshold. So that was the reason you got the lasing threshold so low. Now I'll now go back to another example, as I was mentioning, and I was mentioning that in perovskite you can have wide range of absorption, or and also emission. So the lasing can also be in that wide range, and this is a work also done by Professor Gedda's group. So here the thing is you can actually change the composition of the perovskite to tune the emission. And when you can tune the emission, you can just make some cavity, and then you also get a tunable laser system. So just for one spectrum, let's say here you in 12 microjoule you have this spontaneous emission, and then you keep increasing the pumping intensity, you start to see that there is a kink appearing here, and then if you increase it further, you start to see that the photoluminescence is completely suppressed, and you have this only this part of emission, which we can call as lasing spectrum. And here in this case, the amplified spontaneous emission part is clearly visible. So let's say when at very low power, excitation power, when the power is varied, the photoluminescence is obviously increasing, because you see that there is a signal to noise ratio is quite visible, and then here signal to noise ratio is completely gone. So that means the photoluminescence is increased a lot. Now, if you keep increasing the power, at certain time you will see that the defect levels are saturated, and when the defect levels are saturated, then further reflection will add up to the emission. And then this is now this this is the amplified spontaneous emission part, and when you cross a certain time, and you will see that the emission intensity is amplifying much larger than before, and this is the reason which we call the laser action. Now, as you can see, this is like this is the crystalline structure of the system, and this is nicely hexagonal one. So the light and this is the diameter is now 50 micron, and now you can see that the lasing threshold is also quite less, so like quite high than the previous one. So obviously this can this can behave as light amplifying medium, which we already have seen, but when you are coming closer to the lambda of the order of lambda, then your lasing threshold is much lesser than before. Now, I will give you another example of different kind of perovskite. So previously, I was just giving you some perovskite nanorod and bulk perovskite, and now this is a two-dimensional perovskite. So in this case, this is like not exactly two-dimensional perovskite, but this is a hybrid perovskite. It's a mixture of 2D and 3D. Here in this case, by playing with the ligand, you can actually create some sort of quantum wall kind of situation, and if you keep increasing the distance between the quantum well, you actually can tune the emission of the system. So in this case, now there are let's say 3 different composition which gives the emission in 3 distinct different region. And then because this is highly crystalline, and it create a layer by layer structure, and you can see this the optical microscope picture, it is like really flat, and this flatness is actually giving this light reflecting medium. So there is a light amplification going on in the system, and if you keep increasing the excitation intensity, you eventually get this very strong lasing emission from the system. And by changing the composition of by changing the composition of the system, you can actually tune the emission from the system. So those are very classic example of lasing system. And after that, I will go to another unconventional laser. And if you have any question, you can ask me right now, and then I'll move to the next part. And then obviously we'll have another question answer session later on. So if there is no question, then I will quickly move to the next part. Now, previously I was just talking about, let's say, this conventional laser. Now I'll talk about random laser. So the difference is already clear by the name. So in conventional laser, you have well-defined cavity. It can be a reflector, it can be some nice geometry like triangle, hexagon, or other polygon to actually give really distinct optical path to have the light amplification of same energy. But it may happen, like, if you consider a situation that you have a disordered matrix, just like this. So and if you just put the light in, and if the let's say the particles in this disordered matrix are highly reflective, then what happen that the light will start to reflect in random direction. And this reflection in the random direction can actually create some weird situation. And this weird situation means, let's say there is a reflection from this side, and this reflects to that, and then it eventually forms a closed loop. And in this kind of closed loop, if the constructive interference actually overcome the losses, then this sort of system can also give the laser emission. And this kind of laser is known as random laser. And the name random come from many different reasons. One is obviously the light amplification matrix is random, because this can make a closed loop which can produce a coherent emission, which can lead to laser. This can also create a coherent emission and lead to laser action. This can also create a coherent emission, lead to laser action. Now, for every laser, the cavity length makes it actually decide the emission the emission energy. For example, for helium neon laser, there is one cavity to actually create 633 nanometer laser. For argon laser, there is another cavity to create 514 nanometer laser. But here in this case, if the cavity is random, it can create a random wavelength to give the lasing action. If the amplification can actually create the gain medium. So the cavity is random. That is the reason the emission the emission energy will be random. And then there is another randomness. So this randomness is now directionality. Like in case of this situation, you see the laser is very directional. In our laser pointer, the laser is super directional. You can the laser doesn't deviate. It is just go straight. But in this situation, the light can go in 4 pi angle. This 4 pi solid angle. The light can go to any direction. Now, this is a weird laser, obviously. Now, but then what is the reason of doing this kind of laser? Okay, there are several applications, and the applications are, let's say, we want to have a very bright display, and the display is so bright that we can see the display from 10 kilometers away. I'm just giving an example. So, and the normal display cannot do that. We need to have really some sort of quasi-directionality to see the display. So this quasi-directionality none of the laser can give, because you cannot see the laser. I mean, if you see the laser, you will burn your eyes. Or even let's say you reduce the laser intensity, then you can see the display. Now, display should be seen from every direction. So, and laser is normal conventional laser is highly directional. So the display is visible from only one direction. So if you want to have this super bright display, you need to diffuse the laser. And this is the diffuse laser. Now, instead of super bright display, there are several other things. For example, temperature sensing. We know that, let's say, this is we are talking about some micron range. If we change the temperature, this nanoparticles, let's say, they will start to oscillate, or they will expand, or this expansion or oscillation will cause the change of this emission modes. And based on that, it can it can give a room to produce a temperature sensor. Or biomedical imaging, for example, let's say if you want to image a biocell, you need to have very bright light emitting source, and those are actually those bright light emitting source which are good for biomedical imaging. And then there is even more promising application, for example, Li-Fi. So this is where we need to have to create a strong Li-Fi signal. We need to have very strong light source, and it should be also diffused. Like a strong light source means always laser, right? And then it should be diffused. So otherwise the Li-Fi signal will be only in one direction. So this is again very promising system for this kind of application. Now, let me show you some of the design which I came up with for this kind of random lasers. Here is one example. So here, we have this kind of matrix, and you see that if you consider those are this reflector, mirrors, you see this is really random in this matrix, and this is just only 1 micron. If you see the larger image, it is like this random. Now, if we quote perovskite in it, and then we excite the perovskite. The emission from perovskite can be, multiplied by many different shape of cavities inside the this matrix, and as a result, the light emission can have multiple modes, and this is one of the example for it. Before lasing threshold, if you see the photoluminescence, there is no sharp spike. So in your first glance, you will see, oh, this is a very noisy photoluminescence spectrum. But no, this is not noisy photoluminescence spectrum. It is very strong actually. So in normal case, the photoluminescence is here. And then if you add up to the pumping intensity, you start to see that some peaks start to rise. And then those peaks eventually take very high intensity, which if you plot the, this again, if you plot the pumping intensity against the emission intensity, you will see that there is a very clear threshold here. And again, also for line width, there is a clear kink here, which signifies that this is a lasing, this system is lasing. Now, as I was saying, that the emission should not have any directionality. Now, if you change the angle of the sample with respect to the detection angle, because the lasing is happening in every direction, the system, the spectrometer should still show the lasing emission. And this is where, when we change the sample angle, we see that the system is still showing the lasing behavior. And then this is again one of the key parameters for lasing, especially for random lasing. In case of random lasing, the excitation medium should be larger than the gain medium. Otherwise the emission loss will actually make the system not to lase. To explain this thing is like, if we excite in a tiny region, then the emission, because this is a random matrix, the emission will go to every direction, and all other system are not excited. So they will obviously get this excitation from the previously excited sample, but eventually they will not add up to the emission because as you can see, this is a random matrix. So before the light come back to the system, the light is lost in the system. So this is the reason, you need to have a excitation medium larger than the gain medium. So to give you an example, like if you let's say if you are exciting only this part, and your excitation, the light is reflecting really nicely here in this wall, and you are exciting the whole part, so you will get the laser action. But let's say this is a bigger part and you are exciting only this region, and the other region are guiding the light to other direction, because there are some randomness here, so the light is not properly coming back to the original system. So then it is not possible to see the lasing spectrum from this small region of excitation. Now, this can be proved experimentally, just to make the excitation spot bigger than narrower. So here is the example. So if the excitation spot is narrower, you see the lasing action is still, because this narrower also includes several metrics here. But if you make it a little bit larger, keeping the intensity same, then you see the lasing intensity is even more pronounced, which means there are some much better light amplification loops which are now activated, and that was the reason the stronger emission now pop up. Now I'll go back to another system, which is stretchable lasing. Now this is a bizarre concept for lasers. Just a few minutes, okay? I'll finish it. Yeah, this is a stretchable laser is a bizarre concept for laser, right? And the bizarreness means laser should have a proper gain medium, and if you stretch it, you actually distort the gain medium. So this is not good for laser. But here we did some sort of this kind of experiment, and I'll prove you that the stretchable laser is possible. So just quickly to go through how we design this stretchable system. Let's say you have pre-strained PDMS, and then you coat some 2D materials, for example, graphene, and then you coat perovskite on it, and then you release it. And when you release it, it actually creates this wrinkle structure. And now this is a ACM picture of this kind of wrinkle. You can see that there is a very highly dense wrinkle hills and valleys inside. And this is for two different 2D materials. One is graphene and HBN. And this is the AFM picture. You can see that the wrinkles are really highly dense. Now, if you measure the emission from the system, you can see that the when the system is flat, which is 100% strain, then there is only photoluminescence. When you start to shrink, when you start to release, then you start to produce the wrinkles, and you start to see that the emission, the lasing emission is now happening in both of the systems. Now, in case of graphene and HBN, there are graphene can give an additional losses in the system, because graphene doesn't have band gap, so the threshold for graphene is lesser. Now, threshold for graphene is higher. So here is the threshold behavior. So for example, in this threshold energy, you don't see any emission, lasing emission, but here you see very strong lasing emission, and the same thing goes for this. Also, you can see the lasing threshold behavior in case of intensity and line width. Finally, if you do this strain cycle for repeated time, you should demonstrate that the lasing action is still happening. So here we did the multiple cycling experiment. And also this system, because this is PDMS, it is easily bendable. And here is the bendability of the lasing system. And finally, this is the angular dependence, what I was showing you before. Now, I will give you some broader outlook of the system. So let's say, we know about this conventional laser, that it really needs some, precision of, some precisely designed cavity where the light is amplified. Now, in normal system, actually, in finite temperature, the mirrors, they vibrate, and this vibration of the mirror actually cause some sort of distortion in the cavity, and this distortion actually add up to the emission intensity and emission is feature. As a result, you see the broadness of the lasing emission. Now, there is a novel concept to actually get rid of this temperature limited lasing frequency. Here in this case, instead of having this coherent emission based on the reflection, it is possible to actually create some sort of system where the system itself can be a coherent system, and then your light amplification or the coherence is not limited by the mirror. And this sort of system can actually give more spectrally pure laser action than before, and this sort of laser is known as super radiant laser. So the demonstration of this system has been only given in optical, how to say this, optical atom cavity, where every atoms are actually coherent with each other. But it is possible to do this kind of laser also in solid state. And here with the perovskite nanoparticles, there are a lot of prospects, especially for this kind of perovskite, where there is a very precise size of the perovskite nanoparticles, and also they are phase pure. So those sort of system can be used to design laser devices, especially to overcome the thermal limitation of the lasers. Now, to conclude, so I just have shown that there is it is possible to achieve ultra low threshold by lead halide perovskites. Also, because this lead halide perovskites are actually solution processable, so it can actually simplify the laser design with a and also it can give a room to produce a tunable laser source. Then finally, I was also showing this 2D perovskites to create the laser action from single crystals, then ultra low threshold laser action from random laser action from vertical graphene network, and then finally wireable laser action, and then I was giving an outlook for super radiant emission. And with that, I would like to stop here, and I'll welcome the questions from you. Thank you.
Thank you very much, Haider, for this very interesting and detailed presentation about the use of metal halide perovskites for applications like lasers. So the floor is now open to question and answer. So I cannot see any question. I have some though. Maybe I can start to give some time to the audience. So I would like to start from the last part of your presentation when you used graphene. And also you mentioned something about HBN.
Yes.
Could you please explain? Yes. Could you please a bit explain on what type of graphene are you using for this work?
Okay.
And what is the role of HBN here?
Yes, exactly. So here we are using CVD graphene. So let's say we create a PDMS and then we transfer graphene layer on it. And okay, we have three different materials here, and this is the example showing with RGO, reduced graphene oxide, and then this is with graphene, single layer graphene, and this is with HBN, hexagonal boron nitride, and this is exfoliated hexagonal boron nitride. Okay, so in both of the cases, in case of RGO, the matrix is much more random, and this is the reason we call this wrinkled graphene, but otherwise this is ripple. So in case of RGO, this is producing wrinkle kind of a structure, means the ripples are very random. But in case of normal graphene, CVD graphene, which is like large area, is like more than 2 × 2 centimeter area, so it is like quite large. So you can produce in this kind of ripple structure. And this HBN system actually we produce in in two different ways. One is exfoliated one, which is like pure HBN, there is no defect and all. But we also produce CVD HBN. So we tested in both of the cases. And here there is a large area CVD HBN, and it shows the wrinkle structure you can see right now. If you the perovskite are already coated there, so the perovskite are also in this wrinkle structure. Now if you consider here, let's say if we excite the light, and then the emitted light will go in every direction, and this emitted light will actually hit with another nanoparticle or will go through this boundary, let's say, and during this going through process, it will excite this another nanoparticle, and this nanoparticle, the emission from nanoparticle will probably bounce back to another nanoparticle. As a result, it will create a closed loop in the system. And this sort of amplification will lead to the laser action. And it doesn't really matter whether we have graphene or HBN. If we have if we coat with perovskite, and if the reflection is from the perovskite, and we separate the perovskite layer from this charge transfer to the graphene layer, which we eventually did, otherwise lasing action will not be possible. Then it doesn't really matter what kind of 2D materials you are using. If you create this wrinkle structure, it will eventually lead to lasing action. Now in normal graphene, there is a charge transfer with the perovskite, right? because it will create a band bending, and then you will see, instead of light amplification, you will see the photoluminescence will heavily quench, and you will eventually see there is no photoluminescence at all. But here, these nanoparticles are actually coated by oleic acid. So there is a this is actually bromide perovskite, methyl ammonium lead bromide, and this is not really stable much in air, but we stabilize this one with this oleic acid coating, and this actually add up to the value that even graphene, if you use graphene, it doesn't really quench the emission too much. Obviously, if the oleic acid coating is quite thin, so this is still a question of research. I mean, there can be multiple answer of it eventually. It really depends on how nicely it is coated, and the point is we just need to suppress the charge transfer, which quench the emission. We need to get rid of it, and then eventually we will have the light amplification. And this is for graphene. For HBN is an insulator, which is always there is no charge transfer at all, and it is just good for the system. And this is the reason I was saying that in case of HBN, you see the lasing is much better. So if you go to the threshold, you see the lasing in HBN is much better. Yeah.
But was it, I mean, easy for you to grow this HBN by CVT, and was it like single layer?
This is definitely not single layer. Probably this is not probably, this is exactly 6.3 nanometer. So it's like around, how much? It's more than 20 layers.
Okay.
Yeah.
And have you observed the same exactly behavior with the mechanical exfoliated one?
In case of mechanically exfoliated one, yes, it is giving the same result. But in case of mechanically exfoliated, it is even better. But here we haven't shown the report in this in this particular paper, is because we are trying to show that it can be applied in larger area. So one of the focus on this work was for the larger area. But obviously, in case of mechanical exfoliation is much better, but it should be in a tiny region, and the finding this is really big job. Probably it already, right? So finding this one is really tough. Yeah. But it is very easy to produce actually. Let's say you have this HBN crystal, you just exfoliate with tape and put it in the PDMS. You will have multiple HBN already there, and then you will have those flakes all around, and then you got perovskite and release it. You have it the system, right? Yeah, it's very easy actually.
Okay, thank you very much for the answer. Another final point from my side, and I can see also some questions in the chat, is that in the first example that you presented, the threshold energy for lasing was much lower compared to the other two that you presented.
Yes.
Can you explain why?
Yeah, so this was here, right? Yeah. So the first reason is their phase purity. You can see the crystal here, right? This is really nicely crystalline. And then obviously you see the reflecting medium. It is like perfectly parallel, right? So the reflection is really high. If you go to the other system, for example, here you see this is a distorted hexagonal shape. And this distorted hexagonal shape cannot really make a very nice, reflection or very nice optical interference, right? For interference, you need to have nicely coming back light. Otherwise, the interference will not be good. So in this case, this is nicely crystalline, and also the edges are very sharp and parallel to each other. So the light reflection gives very, very nice interference pattern. You can see it from here even. So you see very nice dot here, right? So those are the hotspot for laser, and this is already clear. So yeah, so I hope I give you
yes, exactly. Thanks a lot for clarifying. So let's move to another question from the audience. In this case, Clara Kieselman. Thank you. I wonder if you could say anything about the stability of perovskites in these applications. We know it is a very sensitive material. Have you encountered any problems?
Yeah, so obviously, I was just giving the same answer, right? To stabilize this one, we use oleic acid. Otherwise, it is not so easy to put this in this graphene matrix, for example, and both of them are graphene matrix or HBN matrix, right? For those experiments are actually time consuming, especially for a stretchable one. So it is you need to align the system, you need to give the strain, and you need to study the system multiple times. And reproducibility is one of the key issue, right? And I was also giving you some data for that. So here, for example, we are measuring in multiple cycles to actually give you the reproducibility, right? So obviously, first we need to stabilize the perovskite. Otherwise, there is no question of reproducibility. Second, the reproducibility also comes from the design point of view. For example, we are actually demonstrating the stretchable part, and in this, during stretching, if we rip the system off, then also it is bad for the system, and we also need to demonstrate the reproducibility for that. Now, this strain cycle reproducibility already give the reproducibility answer for perovskites. We stabilize this one with oleic acid, and then finally we have done those experiments. Yeah.
Thank you very much for the answer. So let's move to the last one from Danish. Nice lecture. Can you give your suggestion on will chalcogenide perovskite nanomaterials useful for these laser applications? Is there specified structure and shape of nanomaterials required for laser applications?
Okay, so the question was not very clear to me, but I guess what kind of, let's say,
maybe I can ask this person to unmute. Give me 1 second,
okay.
And maybe he can clarify. Give me a sec. Yes.
Yeah. Can you hear me, Dr.
Yes.
Golam?
Yes.
Yeah. Thank you so much for the nice lecture. My question is, we are working on some chalcogenide perovskite materials for less solar cell application. We want to know that whether this kind of chalcogenide based is useful for lasers.
Okay, so this is a very good question. Yeah. So the thing is, first, there is some key parameters we need to check. The first thing is how strong the emission of the system is. So if the system emission is already very strong, so that means that also already covered the direct band gap nature, because the first thing is it should have direct band gap, otherwise there is no question of laser, right? So then after that, if the emission is very strong or not. If the emission is already very strong, then obviously this is a good candidate for laser. And then obviously the shape of the particle matters a lot. I was just discussing this with you with few minutes back. If the shape of the nanoparticle is already very nice, then it is a very promising material for light emission, for laser action. Now, if the shape is not good, then it is still a very good matrix for lasing action. And then you need to have an additional matrix for amplifying the light. For example, if it is a nanomaterial, then you can actually mix this up with another light reflecting nanomaterials. For example, let's say surface coated, surface modified gold nanoparticle or silver nanoparticle. This can reflect the light. This can also give plasmonic enhancement. So the laser action is very easy. And in addition to that, you can use this silicon dioxide nanoparticle, which is already insulator and is very highly reflective to the light. So this SiO2 nanoparticle will actually give the hotspot for light reflection, and it will eventually lead the system to laze. Yeah.
Okay, thank you very much for the answer. I cannot see any other question or comment. So thank you very much, Haider, for the very interesting presentation. It gave another very interesting application about this type of perovskite materials. And So it was a very great pleasure and honor for us to have you in our intensive course. So thanks a lot for this. Now we can close this session, and we will come back in at 5 p.m. CET for the last presentation.
Okay.
See
Thank you very
soon.
much. Yeah, thank you.
So, welcome again back to our final presentation, our final lecture of the third day of our intensive course on the metal halide perovskite materials and their optoelectronic applications. It is a great pleasure and honor to have for this lecture with us a very distinguished researcher on her topic, Dr. Wanyi Nie from Los Alamos. So a few words about her. She studied for her bachelor degree on the Department of Applied Physics in the Weihang University, Beijing in China. And she obtained the bachelor degree in 2008. And then she obtained a PhD degree at 2012 from the University of Wake Forest in the United States, again from the Department of Physics. Then he got a postdoctoral position at the same university from 2012 to 2013. Then she moved from 2013 to 2014 to Los Alamos National Laboratory in New Mexico for a postdoc, and then she got promoted to director's postdoc fellow from 2014 to 2016, and since 2016 she holds a research scientist position at the same Los Alamos National Laboratory. So as I mentioned already, it's a great pleasure because she's one or probably the most distinguished speaker on this kind of topic, and she will present to us today her she will explain, she will give the insight about the perovskite semiconductors for direct conversion radiation detector application. So please put your presentation, yes, please, presentation mode and start your presentation. Thank you very much.
Thank you so much. You can still hear me okay, right?
Yes, exactly. Thank you.
Perfect. Thank you so much. Thank you very much for the kind introduction. And it's my great pleasure to be invited to this special event to talk about our research about lead halide perovskite for direct conversion. We also call it solid state radiation detector. And my name is Wanyi Nie. As George discussed earlier, that I am a staff scientist at Los Alamos National Lab at the Center for Integrated Nanotechnology. And I hope after my presentation today, some of you will consider to work with us either through collaboration or as a visitor. So to the topic. So this is an outline for today's topic. I will introduce the background because this is a new audience, so I want to talk about what exactly is a solid state detector. And I will next introduce why perovskite is a good material for some good material or good semiconductor for this application. And I will next talk about two perspectives. One is the perovskite for gamma ray detector, and the other is for X-ray detector and imaging, because these two operate sort of in different operation modes. And if I still have the time, I will talk very briefly about some interesting device physics that we discovered recently, and I want to share you about some results. So first, let me, if I can do the laser pointer. Okay, so radiation detector, first a little background why it is very interesting and very exciting is because we use it in so many different things. For example, at the airport, you always go through a security check, and to see through the luggage, you need some short wavelength X-ray to scan the luggage and look at whether you have a dangerous object. And at the hospital, we all know that X-ray or gamma ray treatment is one of very efficient way of treating cancer and cure cancer cell. And in space science, this is very interesting that people send telescope to the space, to the near Earth orbit, to detect the signal from outer space, to see those stars that are really far away, and detecting X-ray signal sending from those stars are one of the way of looking at how they look at and distinguish what kind of material are on the planets that are very far away. And obviously, the detector are used to detect the nuclear material, to look at the alpha decay or gamma ray emitted when the nuclear processing happen. And finally, we are, as a material science audience, we are all familiar with the crystallography, and use X-ray, we can understand the internal structure of material. So we need some detector to look at the diffraction or scattering signal. So all of these applications need a very sensitive detector. So the detection mechanism, I will take gamma ray interaction with matter as an example. And this is a typical process for high energy photon. For example, gamma ray or X-ray interact with the matter. So just like the photodetector, the incoming photon interacts with the material, ionize a number of carriers. In the photodetector, one photon will generate one electron, and in the forbidden band, they don't generate anything, and above the band, they generate electron. And in the case of X-ray or gamma ray, because they have such a high energy compared to visible photon, they are usually 1,000 times higher in energy, and each photon will interact with the inner core of an atom and ionize a number of electrons. So in this case, one photon will generate a number of charge depending on how they interact with the matter. One way is to deposit all the photon energy to the matter, and this process generates the largest amount of electron. Obviously, you convert all the gamma ray photon or X-ray photon to charge signal, and then you can detect that the charge signal afterwards. And the other is a scattering process. And if you gamma ray hit an atom, and they scatter off with a lower energy, so they only deposit part of their energy on the atom. And in this case, because the deposited energy is much smaller, so the number of charge ionized in this process is less. So by distinguishing the number of charge ionized from each process, you know what is the energy of the incoming photon. If I deposit all the energy through this called the photoelectric effect on the atom, and usually in a certain atom, we will ionize, let's say 1,000 electron. If we collect all the 1,000 electron, then we know what is the energy of the incoming gamma ray photon. And from this process, you know that it is so very important to be able to collect all the carrier. If we have some loss process, then we, instead of 1,000, we only have 900 electron, then it is harder to tell what is the incoming photon energy. So this is the principle of gamma spectroscopy. And there are two different technologies to detect radiation photon. One is called indirect conversion method. So here we use a single crystal, usually inorganic oxide crystal or organic crystal, which have a really strong light emission property. And they are placed in front of the gamma ray photon, and then gamma ray ionize a number of electrons, again, from the previous process, but instead of traveling around, the electron will immediately recombine with a hole that emit the visible light. And we put a visible photon detector behind the scintillator, and then we will collect the visible light signal as the indirect way of detecting the gamma ray photon or X-ray photon. And another way is called the direct conversion method. Here we use a semiconductor, and the carrier electron hole are ionized by the incoming photon. And once we apply a bias, the electron will travel this way, hole will travel this way. So we will collect the charge, ionize the charge directly. So in this process, there are many advantages. For example, in the indirect process, you need, first of all, a very emissive material with a quantum efficiency almost unity to be able to correlate the number of charge ionized to the number of visible photon re-emitted. So that's one challenge. And second challenge is you will see from this little crystal, once you hit the crystal, the light will come from all directions. And that also means that there are many light scattering events in the crystal, so that could be a loss process. So you really have to design a light propagation structure so that you can collect all the light, which turns out to be another challenge. But in the direct conversion technology, you have electron hole ionize. Once you apply a bias, let's assume there's no trap, no recombination center, the carrier mobility is high enough. So once apply a field, in principle, you can collect all the carrier directly without worrying about light scattering or any other loss process. Therefore, a direct conversion detector usually offer really high detection signal and the quantum efficiency, and utilized for high quality data acquisition. So, so next, this is a working principle of solid state detector, also a direct conversion detector. Some people call it semiconductor detector. So here you have an intrinsic semiconductor and sandwiched between p-type contact and n-type contact, making a diode. This is usually a preferred geometry. And once the gamma ray photon comes in, it will, on the path of interacting with this material, it will ionize a number of electron and hole. And if you, because we have a diode and we can apply a bias, and the hole will diffuse this way and the electron will diffuse the other way. So, so that this is a charge separation process. And for gamma ray spectroscopy, for example, and then once this carrier, so each time there is only one gamma ray coming from a radioactive material and generate, let's say, 1,000 electron, and you will see that through interacting through a bulk volume, or take some time for the charge to generate and for the charge to diffuse out of the bulk crystal, and then it will generate a charge decay profile at a certain time constant. And this is called one pulse. And if you, the amplitude of the pulse, so you can integrate underneath this curve to get the total number of charge. And as I discussed earlier, the number of charge is proportional to the number of to the incoming photon energy. So if you are lucky to get this photoelectric effect full energy deposition events, and you are lucky also to collect all the charge, then this area beneath is exactly the incoming energy of the gamma ray photon. And the next, but if we end up with all the interaction process to be a photoelectric effect, we can collect all the carrier, we get identical pulse height at this certain amplitude. Then in the detection spectrum, we have this sharp peak. So this sharp peak is coming from counting the height of the pulse as a function of sorry, this is a histogram. This is counting the height of the pulse, and a vertical axis is the count. So how many pulse at this particular amplitude can you get through, for example, 1 hour detection duration? So if we have all photoelectric effect, we can collect the charge very efficiently all the time. Then we have this single peak corresponding to the incoming photon. However, as I mentioned earlier, that this scattering process is not avoidable. So you will get certain high amplitude pulse, and you will always get some scatter event which give you lower amplitude pulse. So which makes this kind of a structure in a lower amplitude pulse count channel. And usually this, but it follows certain structure, like this competent scattering always have a gradual shoulder, just like the absorption profile, and continue increase in the background. And sometimes depending on your elements, like if you have a lead, for example, and usually the high energy gamma ray or hit the atom, and some characteristic X-ray will be re-emitted. So that will cause a reabsorption of low energy X-ray photon, so which give you several extra peak at the lower energy. So in ideal condition, what people do is to collect all the pulse and then construct a histogram based on the shape. So this obviously look like a peak, so which is located at the highest end, usually correspond to photoelectric effect. and this one look like a shoulder, so it's definitely a competent scattering process, and there will be some other complex structure based on the detector structure that you already know. But on the other hand, if you cannot collect all the carrier each time, is for example, I should collect 1,000, I only collect 600. That means I have some signal here between the peak and the shoulder. And if I have a lot of those, and it's going to merge these two signals together so that you cannot tell the structure of the final spectrum. And that causes a difficulty that you won't be able to count the distinguish the incoming photon very efficiently. So from this process, you know that the semiconductor property of the semiconductor, for example, mobility and the carrier lifetime, trap density are extremely important. And how efficient can we collect all the carriers? So currently, there are many different semiconductors that can be used for photodetector, but not so many for gamma ray or X-ray detector. For example, silicon is a very widely used photodetector material, but it has a pretty low atomic Z number. I think the number is only 14, and it's only suitable for low energy carrier photon detection. And the germanium is one period below silicon, has I think it was 28, something like that, and that have a slightly better detection energy. But however, germanium is indirect bandgap material, so that means we need to operate this detector under cryogenic temperature to remove all the thermal ionized noise signal. And very recently, state of art is called cadmium telluride doped with zinc. This is a solar cell material. This material can potentially work at the room temperature, but there are many shortcomings from this material. I won't get into detail, but the biggest challenge for all of these are the high cost to manufacture the single crystal, because in this case, we really need a single crystal like this big to detect certain appreciable signal or even image the gamma ray photon. But each tiny pixel is costs like $20,000. And in certain case, we need to operate with a cryogenic temperature, so which means we need a liquid nitrogen tank, things like that. That makes the whole detector even bulkier. So it's very inconvenient for various applications. So next, we'll talk about why perovskite is a good material to replace classical semiconductors. So the semiconducting material needed for detector, we have a two level of material requirement. First, the material need to have a high Z element in order to efficiently absorb X-ray or gamma ray photon. And as I discussed earlier, high mobility and long lifetime is a requirement. And then the material need to be low in defect density so that we minimize the dark thermal ionized noise in the dark. And also we minimize the charge carrier loss before we can collect them. And the second, in the device level, we usually need to build a good quality diode so that we can direct the carrier to the correct direction in order to collect them. For example, a PIN diode or a PN diode is usually preferred so that the carrier can travel out more efficiently. And also in the dark, at the zero bias, we have a much lower dark signal if we have a PN junction. And next is that the material must be able to operate stable, very stable under constant X-ray irradiation and high electrical field. Both are pretty harsh environments that the material must be able to survive. And so Halide Perovskites are photovoltaic material that we know through this many days of courses, and they are ABX3 structured semiconductor. So, and one advantage is we can grow them from solution method that most of you already know, that the single crystal can be grown from a precursor in a solution solvent bath, and once we heat them under moderate temperature over a few days, this kind of a cubic like crystal or form, and usually they have a pretty good quality. And these material are low-cost semiconductor that can be grown from low-cost processing. That is one advantage compared to classical semiconductor. And another is their physical property are especially suitable for radiation detector. So from the chemical formula, we know that we have lead, and very recently there are other perovskite structure demonstrated for X-ray detector. They have a cesium, they have silver, bismuth. All of those are high Z elements. So lead, for example, have a Z number over 80, and other element can be even higher than that. So this is a very good, biggest advantage that give perovskite to strongly interact with the high energy photon. So for example, this is a X-ray absorption coefficient calculated for one typical perovskite. This red curve is here, and then this black curve is the silicon. And you will notice there's a big increase in the absorption cross-section for the perovskite material compared to silicon, especially at the higher energy range. So this is a very appealing material compared to silicon for detector. And another is we can grow such big crystal from solution method, and they are the perovskite make really high efficiency photovoltaic device, means the carrier transport property are superior in the material. For example, the carrier can live really long time, and they have a high mobility, and the material is immune from defects. So all these property make the carrier that can be easily travel out of the material to be collected. So which means perovskite are really good material for radiation detector. And before I get into some technical results produced by my group, I want to remind you about a little bit about the device physics of the photodiodes. And earlier I mentioned that it is ideal to make a diode from the perovskite crystal or any other crystal so that the current will flow through one direction. And if we have a photon or gamma ray photon that ionize the electron and hole way above the band edge, and they will relax to the band edge. And if we put asymmetric contact, either n-doped semiconductor or p-doped semiconductor on each face, then the hole will have a direction to diffuse to. So this reduces the chance for recombination, especially in the dark. For a detector, we want no signal, and upon illumination, we want highest signal. This increase the signal to noise ratio. So how do we characterize a diode? Usually we use a current voltage characteristic curve to measure the diode. There are several regimes. Under zero bias, usually if we have a PN diode, there will be a small amount of built-in field, and until at a certain forward bias, it reach a flat band. And after this flat band, there's a turn on in current. The current increase very quickly, so that means we are in the forward injection region. And in the reverse bias, because of this energy offset, so we need a much larger to apply much larger bias to in order to inject current again. Therefore, in the reverse bias, there is a flat region have a very low dark current. This is the ideal region for the detector to operate, because we want very low dark current but a very high photo signal to reduce the to increase the signal to noise ratio. So however, once the reverse bias is high enough, this inversion could happen, which means the electron was flowing this direction, but in this case, it will flow this direction because the field is high enough. The internal field band bending is tilted so much that current tunneling can happen, and many other mechanism could happen which promotes this dark current. And in this region, usually is not a great region to detect low energy, low amount of photon, because the dark current is so high, it can easily overwhelm the signal. But there are other possibilities, like, for example, avalanche diode is operating at the tunneling, this reverse junction breakdown region, which give a really high really high speed, because the carrier can multiplicate. But if I get the time, I will talk about what happened in this region for the perovskite detector that we make. And the next, okay, so this is our results. First, using perovskite single crystal to build a photodiode. And this is a metal ammonium lead bromide crystal, because they can grow into a nice cubic structure. So it's easy to put contact on each side of the crystal, creating a flat electrical field in between. So in the beginning, we deposit p-type contact on one side and N-type contact on the other side, just like the solar cell. So we have asymmetric contact. So we are expecting to build a photodiode, a diode device from this whole stack. And but the only difference is the p-type contact and n-type contact are so far away. So in the middle, we have about 2 millimeter separation between the two electrodes. So therefore, the band bending only happen at the very interface, which is a very short distance. And in the middle of the crystal, most of the crystal are still at the flat band. So this means the depletion region is very narrow, and the middle, most of the part of the crystal have no electrical field, which means the dark conductivity really rely on the dark resistivity of the material. So if we measure the IV curve, and this is the typical IV curve, so we still see this diode behavior because forward injection current is about 2 order magnitude than the reverse bias current. So the electrode somewhat have certain block effect. But if you look at this flat region, we are expecting a very flat region going towards the reverse bias, but we instead we see a pretty good high slope that the dark current increase very rapidly when we see continue to increase electrical field. So this dark current introduce a lot of noise in the dark. So for example, this is a typical detector response when exposed under cesium 662 keV source, which emits I think a 600 keV photon each time, one photon per time. So this is a typical signal that we get from this PN kind of device. As I mentioned earlier, we are expecting this pulse, and we need to count the amplitude of the pulse in order to distinguish the energy. However, you will notice there is a huge baseline fluctuation in a really good insulating device without gamma ray photon interaction. We are expecting a very flat, very low noise baseline if we have a very low dark current. But this large fluctuation is really coming from this huge dark current, which is getting worse when we increase the reverse bias current. So this is kind of interesting because you will notice from the color that the metal ammonium and lead bromide have a 2 eV band gap. So we usually consider it as an insulator in the dark. So, and especially the interface are so far away in the middle of the channel across such a thick insulating device. If we apply several volts bias, we are expecting almost no current. But in contrast, we are getting such a high current once we start to apply moderate field. This is one surprising result that we're looking at. So what's happening is we decide to look at so usually for insulator we are expecting almost the zero current because the band gap is so high, and if we have certain if we have a electron here to excited to the excited state to the band edge to participate the current conduction, then a huge energy is necessary. So the room temperature only provide 25 MeV energy, and this is 2 eV band gap. So this is not the thermal ionization from the conduction valence band to the conduction band. The only possibility is we have so many impurity states in between the gap, so that these are effectively doped states that can be easily thermal ionized to the band edge. That's why we see such a high dark current. However, there are two possibilities. One is either it's a N-type impurity close to the conduction band, so inject the electron, or there are p-type impurity, inject the hole to the valence band, and so we, in order to tell which kind of species is dominating the dark current in the metal ammonium lead bromide crystal, we decide to build electron only and hole only resistor device and look at the resistivity. And it turns out our hole only device have a much higher resistivity. High resistivity means low dark current, but electron device have a much lower resistivity, which means this picture is most likely the case that we have an N-type impurity below the conduction band, and in the dark dark with the thermal energy, thermal fluctuation, or thermal ionization, we have a spontaneous charge injection to the conduction band participating in the conduction, and it's, even without gamma ray in the dark, we have a significant amount of electron-based current. So based on this finding, that we think building a PIN diode may not be a good idea because we are collecting both type of species, and the dark current is dominated by the N-type impurity injection. So we decided to build, just to take this symmetric device, photoconductor, but we only conduct hole through the device to do the detector. And as a result, we see this much nicer shape pulse, and also with a different gamma ray energy, we see a different amplitude. So that is a good sign that the pulse amplitude is proportional to the gamma ray photon. And this is a much cleaner signal. You will see the noise signal to noise ratio is greatly reduced if we block the electron signal from the charge impurity injection. So next, we did some more detailed study, and once we start to increase the electrical field, the pulse amplitude increase accordingly, and the pulse shape get much sharper. And another interesting observation is we see, so this is a very unusual observation from the metal ammonium lead bromide crystal. We see a very slow response. So this is, if you look at the x-axis, the rise time is at the high temperature, and the lower bias is almost is above 100 microseconds. And usually for a good detector, you need a sharper rise time, and they can respond much faster. Like a cadmium telluride detector, they can rise within a micron, 1 microsecond. So this is 100 times slower than the typical classical detector. So this also casts another challenge using the classical instruments, which can only count faster pulse. We can no longer use the same commercial unit for our detector to collect spectrum. So we will have to manually count these pulse and measure the pulse amplitude afterwards, and reconstruct the histogram in order to differentiate the signal. So use our homemade setup. We first measure a CCT detector, CAD-TEL detector, and we are able to look at the photoelectric peak, which is here, and the component structure and the background. There might be some backscattering feature. So although the spectrum quality isn't as high as a commercial available instrument with all the filters and the amplifier, but at least this method is successful by manually count all the pulse. And here is our detector, perovskite detector with a bromide crystal. And we see there are a huge amount of background signal at the lower channel, and we can see kind of a gradual shoulder, which can be corresponding to the competence feature, and some high amplitude pulse are existing at a higher channel number. However, as I mentioned earlier, if you really want to distinguish the photon energy, you must be able to resolve this kind of different structure in order to know, okay, this is a photoelectric peak. This channel can correspond to the CCM source gamma ray photon. But in this case, we have such a blurred structure that we can call this a shoulder. We can even call this a shoulder. So we don't know which one is the photoelectric species. So as a conclusion from our detector, we cannot differentiate the photon energy from the incoming photon. But if you do a calculation, perovskite actually, by material structure, from material structure perspective, it should have a pretty sharp, if operating under an ideal condition, you should have a pretty sharp X-ray absorption peak, gamma ray absorption peak, followed by a sharp competent shoulder. But the reason that we couldn't resolve such a nice structure is we have charge collection efficiency is very poor in this particular crystal, and we still have a charge trapping issue, and we cannot apply high enough field, especially if in this case, we can only apply 100 volts across 2 millimeter crystal at a lower temperature. At a higher temperature, we cannot even go above 50 volts. So this is a big problem, because for the CCT detector to work this nicely, we apply 500 volt across half a centimeter crystal. So obviously, the electrical field isn't enough in our case. So all of these factors contribute to this very poorly resolved spectrum that's not really working. And according to the calculation, if we get a 1% energy resolution, the spectrum look like that. If we get a 30% energy resolution, then it's all smeared out like what we are getting. So most likely our energy resolution is much worse than that. And that's about the gamma ray detector. If I go to the next. So so far we studied the metal ammonia lead bromide crystal, like I mentioned earlier, that the pulse have a really slow increase and very broadened feature. And even under low temperature, 240 Kelvin, this rise time can quickly change. The rise time is much faster once we reduce only 50 Kelvin. So this reminds us about this this temperature dependent processes that this have a very sharp temperature dependence, and by lower temperature just a little bit can increase the rise time quite a lot. So so we decide to look at a different system, which is iodide crystal, metal ammonia lead iodides. And in this case, they are dark black crystal because iodide will narrow the band gap to about 1.6 eV. And we again build a symmetric device. As a consequence, so these are the pulse signal from we collected at the room temperature compare iodide crystal to bromide crystal. I think because iodide crystal, we were able to apply 200 volt without hysteresis or ion migration. So the pulse can be much sharper, and they rise up within about a few microseconds. But it is slow, still a little slow compared to the CCT material in the gray color. So, but one discovery is at a high enough bias for the iodide crystal, there's no significant temperature dependence. So at the room temperature, we have a pretty sharp rise time, and at even 77 Kelvin, we have also a sharp rise time, but it only minimizes the thermal noise. So this also indicates whatever is happening in the bromide crystal, either is ion migration or polarization effect, is absent in the iodide crystal, which means iodide crystal might be a better species for gamma ray photon counting. So I won't get into detail, but because I want to get into the next topic for perovskite detector for X-ray detection and X-ray imaging. So as I mentioned in the background slides, there are many events require X-ray detector, especially at a large scale facility. For example, at the accelerator facility, we studied high energy physics by looking at electron beam bombardment. And at the hospital, we do computed tomography, and at the X-ray diffraction beamline facility, we need a large enough panel to look at the X-ray diffraction panel, and in the space, again, we need a large enough panel. So all of these applications require large enough panel to image the X-ray photon signal. So in this, which means the single crystal we talked about earlier for the gamma ray detector, which only produce like 1 centimeter size area, we need at least hundreds of them to build, let's say, 1 meter panel, and that adds up cost because we need to connect them, we need to grow so many, and we need to pick the right one, which may or may not have the good property. And in the market, there are larger digital panel made with amorphous selenium, usually utilized at the hospital, and usually at these various facilities, they still use the silicon panel, but all of them are pretty expensive. That I know at the advanced beamline facility, one X-ray camera will cost, I think, 1 million or $500,000, and we can use it for, let's say, 10 years, and then we have to replace it. So this is still pretty expensive, and the amorphous selenium, you can make it big enough a panel because the material are fabricated much easily, but still. This kind of panel is very expensive, and also it suffers from low quantum efficiency problem. So this gives perovskite a lot of advantage. And for the X-ray detector application in the field, people have made a lot of progress already. For example, early time, perovskites have a much better have already demonstrated a very good sensitivity of 2000 micron coulomb gray per centimeter square. As a reference, the amorphous selenium only give 1 to 200. So this is already 100 times better in sensitivity or detection efficiency. And later, a very interesting new structure came out with still a high sensitivity and also very low detection limit. So these are the two important parameters for X-ray detector or X-ray imaging. So you want high enough sensitivity to have a high signal to noise ratio, and you want a low enough detection limit so that you can even capture the background X-ray emission. Or at the hospital, you want to lower the dose rate to the patients, but you can still resolve the internal structure. So these double perovskite structure, for example, give a good advantage over the low detection limit side. And also, because these are solution fabricated material, it's possible to make them in a flexible structure in blending with a polymer, so that you can image the patient, for example, from 3-dimension space with a single detector without the need to rotate the patient. So perovskite in this case are very promising material for X-ray detector as well. And we started with a single crystal detector, and this is a single crystal. We put the 2 electrodes on each side. We make a PIN diode as expected. And in the iodide crystal I mentioned earlier, they are much better species than the bromide crystal because it have a lower dark current and less hysteresis or ion migration. So we choose this crystal. And what's interesting is we measure the sensitivity from this single crystal under a 22 keV X-ray source. This is in collaboration with the Ohio State University Professor's House Group. And we obtain a sensitivity of around 10 to the 4 micron coulomb per gray per centimeter square, which is 100 times better than the amorphous selenium panel. But what's interesting is we realized that at the reverse bias region, even though we suppress the dark current, we have a lower sensitivity at this region, 10 to the 4. But once at the forward bias, once we have a much higher charge injection, we actually yield much higher sensitivity to 10 to the 6, which is 100 times better than the reverse bias detection regime. So this was a mystery at that time, and later I will talk about why this is the case. And like I mentioned in the background slide, that we need a large enough panel. So this perovskite have advantage because we can print them over a large area. And ideally, we can even have, for example, silicon integrated circuit readout panel, and we can monolithically print a thick layer of perovskite with a high quality, for example, over a meter scale area, and build the detector from that method. This is a really fast way of building this meter scale panel, and also monolithically grow the material on the silicon readout panel is an advantage compared to, for example, if you use a CATL wafer, you need to bond each of the pixel to the wafer. So that costs a lot of extra work and costs a lot of money. So people have already demonstrated this printable method to build panel, TFT, perovskite panel on the TFT readout channel. However, it's not easy to build a thick layer when you use a solution method. And especially you need to increase the solution concentration. Unlike a solar cell, you need only 200, half a micron thick layer. It's possible to build a single crystal film or even highly crystalline film without so many voids and the boundary. Once you increase the concentration, the crystallization happens so fast. There are a dense amount of nucleation sites. It's very possible you get this porous structure when you use solution method, and also it's hard to get the solvent out. It's possible to get the solvent trapping underneath the film because the crystallization happens usually near the perovskite and air interface. So to solve this problem, I won't get into detail, but this is a 2D perovskite that we use for solar cell, and we think this is a good candidate to build high crystalline layer even when we increase the thickness. And our method is called a hot casting method. So in this case, we heat up the substrate at a high temperature and spin coat the precursor. And because of the high temperature, the solvent go away almost immediately from surface to the bulk. So they no longer dry only from the surface. All the solvent go away even from the bottom. So very quickly it promotes crystallization happen in the film. And as a consequence, we can coat this very large area crystal. But what's important is use the 2D perovskite formula and especially use the hot casting method. We are able to build up to 10 micron thick layer limited by the solution concentration we can get. And if you look at the cross section, we have a really nice crystalline structure across the 10 micron thickness. If you do an X-ray diffraction, you will see this dotted structure showing up in the GX map, usually indicative of high crystallinity. And we decide to use an X-ray beam to scan across 2 millimeter area on our sample and to look at the uniformity. And this is the diffraction peak, 111 peak across 2 millimeter distance. You will see we have a very high homogeneity across our even thick layer. That means the crystallinity is really high and very uniform. So we decide to use this material to build a thin film detector. I don't have much time here, but I want to mention we have a really high dark resistivity at the reverse bias, partially because of high degree of crystallinity and partially because we have a good PIN diode that can deplete the intrinsic semiconductor layer. And as a consequence, we measure the IV curve under X-ray irradiation, just like a solar cell. But in this case, under X-ray illumination, this is the red curve are our 2D perovskite detector, and in the dark, it have a really high low dark current in the reverse bias. Once shine X-ray on the device, we see this signal increase at the zero bias at a short circuit condition, and we even see some VOC from our detector illuminated by X-ray. So all these are measured in the dark. So that once we vary the dosage on the detector, and we have a pretty nice and linear response. Higher dosage have a higher current, and the lower dosage have a lower current. And at a certain point, we reach a limit that is overwhelmed by the dark current. So this dosage number is about 10 to the minus 2 milligray compared to silicon. Silicon already stops around about 10 milligray per second. So our detector have a much better detection limit compared to silicon, so it can operate at a low dosage. And another thing I want to mention is the hysteresis. So because of the high degree of crystallinity, we measure the IV curve under pretty broad range of bias from +5 to -15. And this is actually a hysteresis loop. We see them overlap pretty nicely. And once turn on the light, we also see them overlap pretty nicely. And we see this nice structure, forward injection, flat band, and reverse bias region and the inversion region we can even observe in our detector. So this is a voltage electrical field stability. Once we start to increase the electrical field to higher and higher, the curve can always return to the original point, which means the detector isn't go through material breakdown. And this breakdown is Schottky breakdown that I introduced earlier. And the device made with a 2D perovskite with a hot casting method have a pretty nice good stability over hundreds of hours when we apply 5 kilovolt per centimeter electrical field, but in the 3D perovskite breakdown at a very early time. And finally, we did some X-ray stability study by shining X-ray on the detector, and overnight, the detector didn't show sign of degradation. So this means the device is pretty robust under X-ray irradiation. And next is the sensitivity of the device. And I won't get into detail. It's pretty much some number that I want to mention that with the thin film detector, we are able to get several hundred micron coulomb per centimeter square, gray per centimeter square. This is already comparable to amorphous selenium commercial panel. And remember, these detectors are made by printing method, solution method, which are much lower cost than selenium. and we can scale them up very easily. And finally, I want to show that we can use our detector to image certain objects. We put this shadow mask between light source and our detector and move it around. And this is the photocurrent map collected from our detector. So we can kind of replicate this shadow mask feature. And this feature size is roughly, I think, 100 micrometer feature, or 80 micron stripes. So this is a very interesting detector. And because I'm running out of the time, I will skip the last topic about this device physics. Hopefully I have a future opportunity to introduce this new study. And finally, we demonstrated a flexible device because this is a printable method. We can make them even flexible. So as a summary, I introduced a new semiconductor for gamma ray photon counting. There are many interesting operation physics, and a thin film X-ray detector can be developed from printable method, which enable large area digital panel integration. And we reveal interesting device physics. And finally, I thank the funding from our Los Alamos National Lab, DOE, and the SINC, which is a user center, and we've been collaborating with the various internal and external collaborator to achieve this this work. And with that, I'm happy to take any questions.
Thank you very much, Wanyi, for this very nice, detailed, and informative presentation for our participants. So I would like now to give the floor to the audience for the Q&A session. So is there any question or comment for this very nice presentation? So maybe I can start because I have many, and I will give some time to the audience to think about it. So the first one I would like to ask you is related to the stability of all these X-ray or gamma ray detectors that you presented. So my question is the following. For example, in photovoltaics, we have some specific and particular stability protocols we are using to evaluate, for example, let's say make an accelerated lifetime to predict our device's lifetime for maybe 20 years. Is there any such a protocol for this kind of application?
This is a super interesting question, and I'm pretty sure there isn't a protocol yet, because I think even understanding the stability of the radiation detector is at the initial stage. So for example, we discovered there are multiple reasons could degrade the device. Either there are radiation-induced damage which isn't understood yet. Like if we have a really high flux beam and the material is unprotected, and it's very possible to ablate the material, like evaporate the organics, or any back conversion to the precursor phase could happen in air without any encapsulation. But I think that's a later degradation mechanism. But what's really happening at the early stage is the electrical field instability, and because we know that hysteresis can be very severe if we make a poor quality material, and ion migration can happen if we apply high enough bias. And at a certain point, even the electrode interface could get corrosed by ion diffusion across the interface from the mantle to the perovskite layer. So those are all unknown yet. So what I think is the voltage stability could be the most immediate issue to commercialize these detectors. If we, like I mentioned earlier, the gamma ray detector, we really have to apply 500 volts across the single crystal to get the signal even to start to analyze with. And with a low bias, we always get a very meaningless signal with a lot of noise. And similarly to X-ray detector, the high sensitivity 10 to the 6 value can only obtained at a high enough bias. So low bias can only give us moderate sensitivity value. So without being able to apply high bias, this technology is less meaningful because it loses its efficiency advantage. So I would say the first step to evaluate would be how long can we operate it in under under high electrical field, and how reliable the signal would be, because sometimes it's a complete failure, sometimes it's ion migration that damage the PN junction, damage the interface dopant region, so that we have a gradual increase in dark current or a complete failure. So I think those are all unknown and definitely worth a lot of effort to establish this kind of protocol. So this is a very important question.
Okay, thank you very much. Okay, I can see a question and then I will come back to mine from Danish Babu. Thank you for the very nice lecture. My question is how to determine the barrier height or contact resistance of an appropriate electrode of cesium lead bromide to desirable junctions. Could you please give your comment on this?
You mean determining interface barrier height? Is that what you are saying? So, so there are two things. If you build a diode, for example, here is a diode IV curve. There are two things that you can calculate. Let me go back to this. So this is a resistivity calculated from a dark IV curve. So in a forward bias, once you start to inject a lot of a carrier, so usually there will be a linear region at a high enough voltage. So this is related to the material resistivity. And in the reverse bias, once you build a diode, because you block out all the dark noise, so you have a fully depleted region. So in the reverse bias, you calculate a different resistivity at a much higher value. So in this case, 10 to the 4 giga-ohm centimeter. So this is a combination of the material resistivity plus the diode resistivity. So I hope this is a relevant question. This is relevant to your question, that the resistivity really matters. If you build a diode, you see this IV curve, you can calculate the resistivity at these two regions. And regarding the interface barrier height, I think the very reliable way is to measure the temperature dependence, because for the Schottky barrier, usually the equation is like this exponential curve, which shows the exponential increase in barrier height as a function of temperature. And once you fit this equation, and then you can get this activation energy for your Schottky barrier. So usually that's the most reliable way. But from an IV curve is really hard, because the turnaround voltage depends on many factors. Either this offset in energy or interface there's a little barrier or interface band bending. So by both IV curve or capacitance voltage measurement, you only get a approximate value of the barrier height of the full Schottky junction, but you may not get the barrier height at the interface. So that's only my opinion.
Okay, thank you very much, Denise, for the question, and Wanyi for the detailed answer. There is another comment also. Could you give your comments on reliable detector characterization protocols and further performance improvement in this detector field?
I think this is a great question related to George's question in the beginning, that I think the very first thing to address is this voltage stability issue. And I don't have time to present our recent work. And we found that the voltage instability is actually related to the humidity that can diffuse to the interface. Usually the humidity or diffuse to the interface bound with the defect, which trigger this ion migration. And what we found is if we can completely eliminate the humidity, have a really atomic compact block layer in between the perovskite and the mantle electrode, it's possible to eliminate the junction breakdown possibility and extend the voltage lifetime. And another thing I'm thinking is, according to the recent study, that even with a gold electrode, if you don't apply bias, maybe that's inert with the perovskite, but once you apply electrical field, the gold ion can diffuse to the perovskite layer, which means we really need something to block this interface ion diffusion problem. So that's something that we don't know at this moment, and I think that worth further development. So a protocol would be first to get the detector to operate under high electrical fields without signal fluctuation or continued increase in background signal. So that's my short answer.
Okay, thank you very much for the question and Wanyi for the answer. There is another comment from Thea. Thank you for the descriptive session. What is the reason if the diode is being more as a resistor? How it can be resolved?
If the diode is more like a resistor, is that? I think that this is a complicated question. This could come from several things. Like, okay, first of all, if you have a not such an insulator in the middle, so it's hard to get back to the first slide. Okay, if your crystal is not so insulated, you have so many dark injection, then your diode won't look like a diode. You have such a high reverse bias current, and you have a lot of leakage current. So I think this is especially for single crystal. The quality of the material is deterministic. No matter what interface material you choose, you will always get a leaky diode at the reverse bias. And if you are sure the material have a really high dark resistivity, they are high quality, have no defect, no impurity, then you can think about the interface. So according to our experience, simply putting electrodes, metal electrodes with the asymmetric work function is good enough. Will make a good enough diode. So you don't really need those organic layer at the interface, which usually introduce additional interface that could even increase your dark signal. So we stick with this simple metal electrodes. But maybe in the future, if people find some good metal oxides or any other material that could serve as a better interface material, maybe that will make a better diode.
Thank you very much for the question and Wanyi for the answer. We still have another 3 minutes, so maybe I can ask another question and I will give also the time for the audience to think about any possible other questions. I would like to ask you regarding this, for example, this particular X-ray detector you are presenting here. I can see you have gold as the electrode, right? So I know from the solar cell field, sometimes interfacing perovskite with metals can create problems regarding stability because of this effect of metal-induced degradation inside the perovskite materials. So do you observe the same, behavior in your devices?
Yeah, good question. So if we use so here, for example, we choose lead as low work function metal and the gold as a high work function metal just to make the PN diode. But usually this structure is less stable for if we want to measure them for several hours in air. So lead is a low work function metal, definitely is worse in the air. But with the gold, if we have a dry enough air, if we protect them in a nitrogen filled vial, which is our packaging system, then the gold electrode can survive a slightly longer time. For example, we measure this one for gamma ray detector at 500 volt operation voltage, and we can collect signal for 4 hours without really degradation. But if we measure it the next week, then perhaps there are some problem in that time scale. But in short time scale, few hour time scale, gold is still okay.
Okay, thank you very much. And I can see there is still 1 minute, so I can ask my final one. It is really surprising and exciting to see one of your results demonstrating 100 times better performance than the amorphous selenium. So what needs to be done for the commercialization of this detector then, if it works so well?
Yes. So I think one thing, another thing we discover is, for example, it would be very ideal to monolithically grow this perovskite by printing method on the silicon readout chip, because so far what we develop is a single pixel device with our metal electrode deposited. But really to make an imager, we need to think about how to integrate our material with a silicon chip without damaging to the silicon or introduce defects or noise. So that's one challenge. And another is, can we really transfer our method to this silicon, because it's like you have millions of pixels on the silicon. We need to protect the electrical leads, and we need to also think about how to pixelate. So because if the pixels are so close together, do we have a crosstalk between the two, charge share effect between the two? For example, in the cadmium telluride detector, for example, people have a wafer and they pixelate on the wafer, and which match with the silicon wafer. So they bound these two together with an Indian ball or anything. That's a very delicate process. But if we print the material on the surface, we don't have a way to pixelate the material itself unless some further development of the pixelation technology. So this will introduce some additional issue, so that could be a challenge. But with good quantum efficiency, this is a really good starting point, and we can next think about how to scale them up and integrate with the existing silicon ASIC. I think that's a bigger challenge now.
Okay, thank you very much for the answer. There is a comment from Libitha. Thanks a lot for such a descriptive lecture, very useful. So I think it is about time to close this very interesting presentation from Dr. Wanyi Nie. It was our great pleasure to have you in our school. It was like a very big added value for us, and we learned a lot from your experience. And so thanks a lot. And for the school, we will continue tomorrow for the research skills part of the school. So I hope to see you tomorrow, and have a good night. Bye bye.
Thank you very much. Bye.
Bye bye.